It is on. Okay. So, hi everybody. Welcome to our second meetup. Today we have Axel and Jarrod presenting our migration from Postgres to Cassandra, and then we'll have Johnny Miller from Datastax. And by the end, we'll still have time for a little Q&A or meet the expert since he's here. We don't really have a fixed time, so you can go slowly or it's up to you. But hey, thanks for coming.
Okay, check. Yep. Thanks on my behalf also for arriving and listening to what I have to say. So let's just, check. So I'm Axel, and Jarrod is here. He's the one guy who knows stuff. I'm the guy presenting stuff. And during the presentation, feel free to comment on anything or ask anything. I'll try to answer as good as I can and leave the rest for Jarrod. So without further ado, let's move to Postgres and Cassandra and take this guy out of the way. So in 4 easy steps. 1, 2, 3, 4. First, we have Postgres. This is our old database. We're moving to Cassandra, or have been moving for the last year or so. And 3, we did some magic in between. And 4, we got some profit out of this. So when you have 4 steps, you always start with step number 0, so that you get to 5. So let's talk about the context of what we do here at F-Secure with our database systems. So you probably know the company. Somehow we do security stuff. The stuff that me and Jarrod do is categorizing the internet. We have backend systems storing hundreds of millions of URLs, data types in terabytes. We store reputation about URLs, what kind of sites these things are. Do they contain malware? Are they malicious? Are they gambling? Are they adult sites? And we try to categorize as much as possible, but because of hardware limitations, we take a subset. So we have hundreds of millions of URLs. Google indexes 1 trillion pages. Netcraft surveys 1 billion pages. So with our move to Cassandra, we hope that we can increase the size easily. That's one of the things, because we have limitations in Postgres. So currently we're on hundreds of millions. We want to go to billions. We have this data. We do some automating processing on the data. We crawl URLs, check what they contain, recrawl them, check what they contain tomorrow, the day after that, see if they change, see what rating we give them, and push that out to our customers. We do it for hundreds of thousands of URLs every day. We have multiple services checking different aspects of URLs, and each service is a cluster in its own. So I have hundreds of servers processing data, all accessing the central database. And downtime is not an option for us. So when thinking about the migration, we can't just shut it out for a week and switch over. We have to keep churning day and night to keep the categorization of URLs up to date with their actual content. In addition to the automatic processing, we also have analysts, actual people who look at the data, figure out what patterns we can see, what new rules we can make to have the best categorization possible for the URLs based on the data we store. So we need to have data mining capabilities, researching capabilities, and reporting capabilities. So what this means is we need to have an efficient way to access any part of the data. We need to have efficient queries. We need to provide the analysts with tools to mine the data and do whatever they want to, like random poking around. We never know what they come up with next, some aspect that they want to search from the data. So that's basically why we have this vast system, this vast database. 1, to have the automated processing of refreshing the categorization, and 2, to have the research capability for our analysts to make the rules that the automated processing uses. So going to the current life or the old style of doing things. We have a Postgres database. It's highly normalized. It was built, I don't know how long ago, many years ago, 10 years ago, 5 years ago. So then normalization was a big thing. We wanted to store as much data in as little storage capacity as possible, so we normalized as hell. And that means that we can store a lot in a little space, but makes it really hard to do queries and really hard to make the schema or change the schema, because it's a really stiff thing. You have to define all the columns, all the indices, all the tables, and the relations between those. So adding anything new becomes a pain. That's the price you pay for normalization. Since we're doing Postgres, we need to do the sharding. We did it like a boss. We split the key space of our hashes, of our URLs, into 8 boxes, so that we get the performance of scalability, and also splitting the load mainly. But the problem with that is that each one is a single point of failure. We didn't have any backups for the actual data nodes, and of course it's possible to do it in Postgres. It's not a problem, but that then brings more maintenance work on keeping all those things in sync and running and testing them. And with this single points of failure, also upgrading something causes a downtime for those nodes, and we didn't do many updates on the Postgres database for these reasons. And the third thing with Postgres is that we need to index all the things. If we want to provide searches for our customers or for our analysts, then we need to manually define indices for each and every thing. So the building the queries became a hassle. We needed to have our own query language. We needed to map those to the relational database and provide indices. And there was many layers for each and every new query that we wanted to provide. And researchers being researchers, they come up with new things to do. So we kind of wanted to get rid of these limitations. And we did it by moving to Cassandra. And the things that we did, or the main reasons for going to Cassandra, was the scaling up. Like, we have a subset of the internet categorized in our current database, but we want to grow larger. We want to be able to scale when we get more money or more funding. We can buy new hardware. We can scale up easily using Cassandra. In Postgres, scaling up was hard because we had the fixed sharding. If we wanted to scale up, we had to double and double and double the splits, or the number of nodes. Yeah, the number of backend nodes need to be doubled so that we can easily split the current partitions. But with Cassandra, we get the load balancing and clustering easily done. We get replication done. We don't have to have as much downtime. We can upgrade one node at a time and use the replication steps. Yeah, and since we're doing kind of this DevOps stuff here, so me and Jarrod are directly affected with anything related to maintenance on the Cassandra cluster. So that's why we also want it to be as easy as possible. So when moving to Cassandra, we need to do some mapping of our data. Of course, in relational databases, we had loads of tables and columns between those, and foreign keys between the columns to map our highly normalized data. In Cassandra, we use NoSQL, of course, and we need to restructure all our data. Luckily, the structure is quite feasible, or the structure of our data is quite usable in Cassandra. It's mostly single URLs and data on those single URLs. So given a URL, give all data we have on that, or the categorizations of that URL, or some specific metadata. So for NoSQL, the URL becomes the row key, and then you just have loads and loads of columns on that key, which of course makes it quite easy to do the mapping. But when moving from relational databases to NoSQL, you don't have queries anymore. You can't do selects in the same way. So what we did, we created our Cassandra schema in order to provide these fixed pattern accesses that our automation running in the background will use. So building the columns in such a way that the data that we need to fetch is available and easily queryable or fetchable. So Cassandra has this column ordering that is really handy when doing this. So for example, if we have timestamp data, we can put them in column orders and then get the latest 10 values from a longer list without having to iterate through the whole list and check stuff. And since Cassandra doesn't offer queries, we opted to go for Elasticsearch in the research part. So the analyst will be using Elasticsearch for querying data in our database. Of course, we could have gone with Elasticsearch on top of Postgres, but since we already had gotten stuck with the notion of relational databases provide querying, so it didn't really seem feasible at that point to have a separate index and a separate data storage. Since you get it for free, why not use it? But now we have them separated, and the load on the other one doesn't affect the load of the other. So we can have heavy queries without affecting the performance of Cassandra, and we can have heavy load on Cassandra without affecting queries of the performance. So we kind of keep them separated, which is a really nice extra benefit here. So doing the denormalization of Postgres data to Cassandra is that we have this fixed pattern access that is used for the automation. So relations from Postgres databases or Postgres tables become columns or sets of columns in the Cassandra database in our implementation. So for example, if we have a URL in our old database, a URL would map to one or more categories, for example, adult or gambling or so on. So now instead of having 2 column families or 2 tables, we just put all the categories into columns in our Cassandra column family that stores the URLs. So you will probably be talking about SQL and collections in the next presentation, but we started our work before this feature was available, so it's kind of the same thing, but doing it manually, and in that way we also have more control of the format of the columns. And what we also need to do when denormalizing is that we need to minimize the amount of these read and then write scenarios. So almost all of our updates to the database are just blind writes to maximize performance and to minimize the problems of not having transactions, of doing concurrent reads and concurrent writes that would store the wrong data. So give an example, or visualizing the example I mentioned. Up top we have a Postgres model or schema for mapping a URL to a category and vice versa. Down below we have the Cassandra column families for URLs and categories, storing the same data and providing the same core queries. So in Postgres we have a URL, it has a key and it stores the URL as a string. We have categories, it has a key and the name of that category. So in traditional relational databases, we then have a join table here that joins URLs to categories so that we can have many-to-many relationships between these two. And it works, but then if you want to do the query from a URL and a free-form string query on the category, then you see that it will be a lot of joins and a lot of querying. In Cassandra, when we mapped the URLs to categories, a URL has the URL key or a hash of the URL as the row key. We store the URL, and then for each category we store one column prefixed with some category name prefix, so that we can do a fetch with this prefix over the columns in Cassandra and then only get the categories, or even do paginated access on the categories, getting columns starting from this one and taking the next 10 or 100. And then in the actual cell or content of the column, we can store a timestamp or any other metadata that is stored for the linking of these two resources. And to get the reverse queries, we have a separate column family for categories, which contains all the URLs that have been set as categories. So then we kind of, without needing to rely on external indices, we can get the basic operations on these relationships all in Cassandra, and they are quite performant. Understand? Kind of? Of course, we have some more complex stuff also, like it's always not this easy to do the mapping if we have had some problems with larger datasets, but this is the basic operating or modeling that we've been doing for getting rid of the relational databases. So in practice, what did we actually do when switching from Postgres to Cassandra? So we had this going into production. Before going into production, Cassandra was really new when we started out. We wanted to test it before committing to it. So we have a data access layer for all the systems, and which abstracts away the database. So what we could do is we could run two databases in parallel. We have Postgres and Cassandra, and we just started implementing our new features into Cassandra. Somebody wanted to store some new data in our database about the URLs. Okay, let's just write that stuff to Cassandra, and when accessing it through the data access layer, just query both databases and join the results, and off we go. So this is a really good way to get a feel of how Cassandra works, what the limitations are, how you want to model the data, and what the performance will be, what the scalability will be, what resources you will be needing to run that stuff. So it was a really good way to get a feel of Cassandra before actually committing. As I said, downtime was not an option, so we couldn't just implement everything in Cassandra and then flip a big switch and see, oh, it didn't work as we expected it, and then have to switch back and fix every problems. So a bit more detail on our two databases. So everything runs in parallel. When we write to one, we write to the other one. We keep them in sync so that it doesn't really matter which one we read from. And when keeping them in sync, we can also do the verification. So we read, when we write to both. When we read from both, and then we cross-validate the results, checking that the data is stored as it should be stored, and that we're not losing any data in the serialization of the stuff, or that it's not in the wrong format, or missing some UTF characters, or whatever might be the case. And then when we have the reads from both, and we are sure that they're the same, we have been validating it from thousands and thousands of reads, we can start switching certain parts of the data reads to only use Cassandra. One by one, we can start moving to the new format and then dropping off all parts from Postgres. So it's this seamless, continuous migration from Postgres to Cassandra one by one. New or single parts of our database. So actually, what we did, or all in all, the 4 steps in the end was we just dump all our keys from a Postgres database. We have the hundreds of millions of things. Once we have everything in sync and all the new writes will be going to both databases, we can just dump the keys from Postgres, and for each key, read the latest data, delete any old data that we might have in Cassandra, and rewrite the new data into Cassandra. And because all of the previous writes, all of the new writes will be written to both, we can assure that after this operation, everything will be in sync. And of course, we can do some validation and checking the failing URLs in the logs and see why they were failing, whether it's just some garbage stuff that has been left over, and so on. And then we do the final cross-validation, and then we're actually quite certain that the data is the same. Of course, when you have hundreds of millions of data points, there will always be some outliers, and you have to check those and see if it's actually something worth storing anymore. It might be garbage from years back or some testing data or so on. So that's basically the migration. We gain some profit. We have a new database. It's faster. It's more scalable. It's easier to expand on. We got some tips from what we actually been doing, and anybody following in our footsteps might want to consider. So first of all, decide what you don't want to migrate. Like, we had a lot of data that we actually didn't need, either be it columns that you actually don't use anymore, or metadata that you don't need anymore. You can just drop that. Or then if you can do some filtering on the actual rows of data that you notice that nobody's accessed for a long time, or you don't have a value. So now it's a good time to do some spring cleaning in the same go. Of course, you want to be testing it. You want to dry run while testing, just reading everything without doing the writing, or simulating the writing to something else, or writing to the database but then dropping it later. And when doing that, both keep an eye on the performance of the actual migration and the database you're writing on, but also the database you're reading from, so that if you do put a heavy load on that, then it might affect the services that you're running. And if you see performance problems, of course you want to throttle it in some way, limiting it and how many rows you read per second or minute, and then just take some more calendar time to actually do the migration. And of course, it's good to start in small batches. Even when doing the final migration, you do one thing at a time, or one batch at a time, and check that it actually went through, there were no problems, and then go on and starting more batches and doing it in parallel to speed up, because hopefully both your databases are able to work in parallel as efficiently as possible. And everything doesn't go as planned, or hardly ever. So when deciding on how you do your migration, you probably want to be able to re-migrate again. You want to have your script be able to, you can just run it again when you noticed, oh, we forgot this column, oh, this column is in the wrong format for some reason. Then you want to be able to just do a re-migration, copying the old data in its original format to the new database without having to drop the whole new database or having some other major operations on that. And also ensure that the actual cluster you're migrating to will handle the load. Even if you tested it with some data, it might, like if you tested it with small amounts of data, it changes in behavior quite rapidly when you throw hundreds of millions of URLs. We got some issues with that, and we needed some extra time to take care of those issues so that we got the performance that we wanted, or the performance that we were used to with the smaller databases. Yeah. And all in all, that's it in the 4 simple steps. Thanks. So, any questions or comments? We have a microphone here. Maybe Bruno can run around and poke it in people's faces.
You need to talk quite close.
Hello, I'm Niklas. Thanks for a good presentation. Yes, I'm very interested in the indexing and storing of the data in the tables. If you could go back to that slide, if possible, so it's easier for me to explain. So about how you store the categories with the URLs.
Yeah. So you mean this one?
Yes.
Okay.
Yes. So do you store the category names and then all the URL keys in that same row.
Yeah. So
okay,
this
so you add a lot of columns there.
Yeah. So it's a row with huge amounts of columns, but
yeah,
in Cassandra that is not a problem. You can have millions and millions of columns, and when you fetch those columns, you probably don't fetch all of them at once. You do some pagination if you are batching so that you don't block the call for a long time. But basically, you can put a lot of columns.
Okay, thank you. That clears it up a lot.
No problem.
What's the motivation for having all the category? Like if you have adult, for example, you can expect it to be a big portion of the total URLs if you're categorizing the internet. Why go for such a, let's say, a waste of space and not try something else like sampling? I mean, what use do you have for knowing?
Oh, you mean why we need the reverse mapping from URL to category and from category to URL? Well, usually if we want to do some operations on specific categories, like we want to iterate through the category and update some data, or maybe do some reprocessing of all URLs that have been marked as malicious, which is, of course, a site containing something bad. Maybe we want to do more frequent checks on those categories or those ratings. So that's why we kind of, in Cassandra, want to have the two-way mapping so that our automation can work on these sets really efficiently.
What is the biggest amount of URLs you have per any single category? Is it hundreds of thousands or millions or?
That's a hard question, but I can imagine that there would be a category that contains almost all of our URLs in the database. Jarrod maybe has a better hunch, but it's in the millions.
Yeah, it's probably in the millions, I would say.
And I don't think we have had any performance issues with having a lot of stuff in.
Yeah, especially like with the since you can paginate very easily through the columns, so that has really saved us.
That's true.
Yeah.
And there is no issue with this.
No, at least we have not had it. At least not so far.
The reason for using the mic is that we have F-Secure country offices online from Russia and in Oulu and in Kuala Lumpur, and that's why we are also recording. That's why we insist on using the mic. But there was a question here.
You mentioned that two databases are still in production in parallel.
Mm-hmm.
So how much load does Cassandra sustain at the moment?
Well, Cassandra can take the load more easily than Postgres actually. So if we have, I'd say at the moment when we got stuff tweaked up, but Jarrod can maybe elaborate.
Like with the write performance on Cassandra, we've not had any issues. We use SSDs for the commit log, and initially we had just regular disks on the for the data, but then we switched those to SSDs because we had troubles with the disk I/O and reads from the services. So after switching to SSDs, we've had no troubles with disk I/O on the reads either.
So how many transactions per second? What is the split, especially how often do you update the records?
The writes are like, well, I don't have any numbers, but it's like happening all the time. I mean, I don't know, to be honest.
Yeah, if I remember correctly, we have like a few hundred operations per second, both read and write.
At least we import, was it like some hundreds of thousands URLs per day? It's in the hundreds of thousands of URLs. So
yeah, of course, importing one URL will trigger a bunch of different services which will read the data and write to the data. But maybe Bruno is already getting some data.
I guess I have a question of like a little bit more specific. How often do you update or delete data?
like for the deletes, we don't specifically delete at the moment, but we rely on the TTL to kind of clean up old records. Like, so they tombstone out and then they get cleaned up in the compaction, or?
And even more concrete questions from my personal experience. So, tombstones, they, at least in our case, they tend to be a problem. Sometimes you just cannot get rid of them, regardless of GC grace you set up, or even if you're trying to do manual cleanup, you still, find some old records. And if you have seen this kind of problems. And the second one is, and one of the reasons I'm asking between balance of reading and writes, in probably last 3 or 4 months, and we are using 1.2.6 in development, because we are doing performance testing at the same time as we develop. We were able actually with 100,000 records, but with specific pattern of writing and reading, it was very short interval between write and read. We were able actually to corrupt tables. If you have seen anything like this.
Actually, no, and we're using 1.2.13 quite recently. We upgraded. What else?
Yeah, but one thing, our data is really static. We store data about URLs. We don't have that many deletions. When doing the migration, we had a lot of deletions, and then we had a lot of tombstones, and then we had to kind of clean that up, put some manual effort to it.
And we also run repair on the nodes once a week, so that maybe that helps with the situation. I'm not sure.
Yeah, but we can ask the expert then in the Q&A session after the presentations. I got some data from our online viewers, and it says 1,500 writes per second, 1,100 reads per second from the last 5 minutes. Our guy upstairs was online. So that's the load. Yep. Can you take the mic, please? Guys online also will hear the discussion here. Thanks.
So are you using secondary indexes at all, or not at all?
Just one index.
Okay. Did you experience any like hiccups with that, so that it just get messed up when you delete stuff from Cassandra?
Well, as mentioned, we don't have that many deletions. Most of our data is just appending new stuff, writing new categorization for the URLs, writing new URLs. So deletions hasn't been a problem for us because of our domain, but we don't have any silver bullets for fixing delete problems, maybe. The experts have some comments on this.
I'd be very worried if you're having. Sorry, who said that? I'd be very worried if you're having problems on things deleting or data or corruption on your schema or tombstones coming back. That definitely shouldn't be happening. I would say your problem sounds to me more likely to do with. I would be thinking drift between your servers, time becoming out of sync, or potentially nodes being out for the. I'd be very interested.
We used to have this corruption even when we have the run node on the same machine or local cluster.
Yeah.
So there shouldn't be any problem.
I mean, I'm actually going to go into it in my presentation as well. But I mean, secondary indexes, when you apply them to column families in Cassandra, I mean, they're not a very performant option. It's not something to use if you're going to be querying that kind of in anger, because if you think about what it's actually doing there, it's going out to all your nodes doing it. So, but I'm quite happy to spend some time with you guys afterwards and find out a bit more if you want. But data corruption, schema corruption, this does not happen. There must be something else going on. It might. That would be very odd as well. That's either something environmental causing that problem, or there's a bug in Cassandra. And you're both on 1.2.6, or? Yeah. But no, that would worry me. Sorry.
Okay, more questions related with this presentation? No?
want to know about the hardware actually currently like using now. What kind of hardware you have? Like, is it combination or all in SSD or just only commit log in SSD?
We have the commit log and the data in SSDs. It's two different partitions for both. And the data stored in RAID 0 SSDs as well. I don't know if it makes too much of a difference, but we wanted to like minimize on the disk I/O if there was going to be any, because we had issues with reads on HDDs before. So
still regarding those categories and storing all of those in the same place. So I was under the impression that all the data for a single row needs to be stored on a single server, and also that there's a 2 billion entry limit. Is that the case, and do you foresee any problems from that?
Yeah, there is the data limit of 2 billion, but we don't store that much data at the moment, and we'll have to figure out what to do if we hit that limit. Maybe split one category into 2 rows and just have the first billion in the one and second billion in the other one. And yes, the whole row will be in a single node, but we haven't seen any problems with that. It's not as if we do a lot of reads on the same rows anyways. Like, it's processing one URL happens maybe once a day at most, so we won't be having. So the load is always split against on all the nodes quite naturally from the way we process the data. So we haven't seen any problems if having hot rows or hot nodes, because all of the data in one row will be on one node.
Okay. There are a beverage and some cake over there, so while we switch the mics, you guys can grab something to eat. 5 minutes. You can also go to the bathroom and stuff. Congrats. You got that thing stuck? I told you I have a machine that cuts that.
Test. Ha! Can you hear okay? God, this. I feel I should be in like khakis and, you know. So where's mine? Sweet. Perfecto. All right. Yeah. Mine is going to be just randomness.
Everybody's have a lot of questions, as you see.
Yeah. You guys, you should check out the lot of the interviews on Planet Cassandra. You can see it's I every day I just go on and start looking through them. It's nothing to do with Datastax. You just see all the different. Yeah, it's genuinely fascinating.
We are also on Planet Cassandra, our use case.
Yeah, top of the list.
No, because we are F, so no.
Well, it's security is one of the whole. I mean, we've got our. It's becoming one of the most popular use cases for us. Can't really say too much about it, but. I've got water there.
Okay.
All right. Okay. Can you hear me all right? Is that all right? All right. Well, thanks to F-Secure for hosting this meetup. It's always great to seem to spend my life traveling around lots of countries, and it's always nice to see companies actually helping the community around Cassandra. So my talk today is whatever you guys, however you want to, what direction you want to take it into. I'm quite happy to drill into stuff in more detail. If you have any specific questions as I'm talking, just go for it and let me know. What I'm looking at covering off is just a brief introduction about Datastax, who we are, a little bit on CQL, very, very high level view of CQL. There's a lot more to it. I'm going to go into some of the typical things around data modeling with CQL. What are the kind of considerations? I'm going to dive into a little bit more detail on time series sensor data, and lots of approaches to take there. And if we have time, I'll also dip into the Java driver, which is the way of doing it. So, God, that's a terrible photo. So that's me. I'm a solutions architect at Datastax. If you want to find out, there's our URL and Twitter and LinkedIn and my email address. I'm always happy to get emails from people asking questions or stuff like that. So don't feel, I like this, and I like knowing interesting problems people have, because it educates me as well. So just to introduce Datastax. So Datastax, we were founded 2010. We're primarily, as I said, we pretty much drive Apache Cassandra. We are got 400 customers, 200 employees. It just keeps going up every year. The company was set up by Jonathan Ellis, who's our CTO. He's the Apache chair for Cassandra. Our headquarters is in San Fran in the Bay Area, and we've got a European headquarters in London, which is where I'm based out of. A little bit of marketing stuff, but just so you know what we do. So what we do at Datastax is we employ loads of developers to work on Apache Cassandra. We roughly 80-90% of the code that goes into Cassandra comes from our developers. We have a bunch of Datastax Community Edition. That's just a slightly easier packaged up version of the Apache one, but it's still just the same one. We have tools like Op Center, which is a kind of a nice management tool for your Cassandra clusters. Dev Center, which I'll show you a little bit later. We also write a bunch of drivers and connectors for the native protocol. And we got lots of free training as well. You should have a look if you're new to it. It's actually pretty good. Bunch of documentation. And then for companies that want that kind of warm blanket around Cassandra, we provide Datastax Enterprise Edition. And what that consists of is essentially a version of Cassandra we've certified, that we can test, that we can support. We've tested it, we've benchmarked it, we've pen tested it, we've patched it, we've fixed it. Any issues are found. These patches make their way back into the Apache project as well, but it just takes time based on the release cycle to come out. We have an analytics piece that sits on top of Cassandra, and we also have a search piece that sits on top of Cassandra, and we've kind of beefed up a lot of the security that you don't have in the Apache version. We also have a slightly richer version of Op Center for Enterprise that lets you do a heck of a lot more. And we provide expert support and consultants and training. So go and have a look at our website. I always bring this one up just to kind of keep an eye on it and see how Cassandra adoption seems to be faring. We're seeing it's becoming just crazy popular. More and more people using it. It's other than Mongo, we're pretty much the best one, and I'm definitely not going to start going on about Mongo. But yeah, I mean, we're seeing adoption of Cassandra just like massively growing. We're like 200 people like Datastax now. When I joined, it was under 100, and that was only a couple of months back. So it's just explosive. We're just getting crazy usage, and it's brilliant. and it reflects in just the really the diverse nature of the people using Cassandra and Datastax Enterprise. This is way out of date. There's more. If you're interested in finding a little bit more about the Cassandra and use cases and companies using it, do have a look at Planet Cassandra. This is the community site. There's some really interesting lists of like 5-minute interviews with everybody, different companies using it, etc. So moving on to the interesting bit. So data modeling. So data modeling seems to be, certainly in my experience, apart from the environmental operational side of stuff, it does seem to be something that a lot of people find difficult to get used to, because the approach to data modeling in a distributed database is completely different to what you would need to do in your traditional kind of RDBMS master-slave type approach. I mean, Cassandra is as I say there, it's optimized for non-relational data models. You cannot do joins, yeah, and it's obvious why you can't do joins. It's a distributed database. If my data is residing here and my other data is residing here, and I want to do a join, this is just going to cane your performance. Similarly with locks and transactions, we have lightweight transactions, which I'll talk about a little, but we don't lock. We don't. If we were locking on reads or writes or anything, or big batch transactions, this won't scale. It just does not work in a distributed database. So you really have to look at a different approach to solving your problems. And there's tons of information out there for you to get. And as I said, I'll go through some typical points that you can have a look at. So SQL. So SQL was introduced a few versions ago, and it stands for Cassandra Query Language. If you know SQL, you know SQL. They are very, very similar. But don't be lulled into doing the same things you would do in SQL as you would do with SQL. You have to still be conscious of the type of database you're using. It's a distributed database. Within SQL, these are just some various terminologies. Key space, that's like a schema. And when you create your key space, which I'll go into in a bit, you set up various information about your key space, how you want it to be working and stuff. Table, exactly the same thing. Thing to note there, as with a relational database, you've got to have a primary key, and you can, when you're querying a table, you can obviously connect up to a key space, or you can use a fully qualified way to get to it. So we have a thing called Dev Center that you might want to look at. It's a much more easier way. It's completely free to download, and you can use that to just start playing with SQL, all this syntax highlighting, stuff like that. A lot of people in Datastax have come from companies that do a lot of tooling around database stuff. So, our people from Quest Software, Toad, stuff like that. So we're constantly building up the kind of tooling around it. So have a look at Dev Center, completely free, and very interested to get people's feedback when they use it. If there's anything you see there that you don't like or any suggestions, just let us know. So, getting into SQL basics, you've got pretty much the same statements you'd have with SQL. You can create, you can drop, you can alter tables, and you can select from them. But you've got to be very conscious of inserts and updates. They are essentially the same thing. Think of it, as I said there, think of it as an upsert when you're inserting data into Cassandra. If the data already exists, it will overwrite it. If it doesn't, it will insert it. So you need to be conscious of that, because we don't give you back a primary key value violation. So we will just override it with the latest version of the data. Okay, so just be aware of that. And the thing that's also very important to note is we don't do any reads before we do writes, which is one of the reasons why our performance is great. So, creating a key space. When you create a key space in Cassandra, this is where you're essentially defining the contract for your collection of tables. The main thing to look at is what you set as the replication strategy for your key space. Right now there's two. There's the simple strategy, which is really a very, as the name suggests, it's a very simple strategy. I wouldn't advise anybody using this in anything other than development or QA. You will get to a point where you want to be slightly more aware of the network topology you're on, the hardware you're on, and using simple strategy basically negates a lot of the high availability aspects of Cassandra and where it places data when it's distributing it around your cluster. So what we usually do is you have a network topology strategy when you create your key space. So what you're doing here is, imagine this is the case where I've got two data centers, yeah? So I've got, I don't know what SD stands for, and TX is probably Texas. So I create a key space here, and I say, use the network topology strategy, and based on network topology strategy, I want to have 3 copies of my data residing in data center SD, and I want to have 2 residing in data center TX. And this is a contract that Cassandra will always honor to the best of its ability. People get confused around the consistency aspect of Cassandra, and they think if I'm writing with a weak consistency, this means my data won't go where I'm telling it to. It will. Cassandra, this is its job to make sure when you tell it, I want 3 replicas in there, 2 replicas in there, it will do this. And there's lots of error handling and failure handling around that, how it handles, losing connectivity in your WAN or nodes flapping, things like that. But it does this for you. This is its job. Very, very cursory view of this, so if anybody has any questions.
So basically, if you don't have network connection to Texas in this case, what typically happens?
So, and this happens a lot, yeah? I mean, we get people's WANs blowing up or data centers blowing up. It will basically store hints, and it will replay these hints back when the data center comes online. And Cassandra has a very simple way of figuring out who wins. It's just based on timestamp. So you will continue to write. So your client could be writing to both these data centers at the same time. When they come back online, it will attempt to replay them, and the latest write will win.
Okay, and you could have these, of course, one in US and one in Europe, maybe.
Yeah, I mean, this is its strength around Cassandra. I mean, the way it handles availability is exceptional. I mean, there is no downtime when you're using Cassandra. Even when you lose WAN connectivity, you have your data centers blowing up, you'll continue to operate if you've structured things correctly and you've put in a certain degree of replication that you can honor whatever degree of consistency you want to have. And also worth noting, there's a lot of tuning you can do between communications within your cluster within data center, but also within data center to data center communications very much at the TCP level. You can enable compression, you can have larger packet sizes, you can do all sorts of cool stuff. You can also tune how sensitive Cassandra is to your network. So if you're running in, for instance, AWS, where your network can be kind of flaky, you can tune Cassandra to say just be a little bit more tolerant of marking nodes as offline. So it can be, but basically it's very, very tunable, and you can tune it to however much you like. I mean, this is it's a shame. This is not really good. This is really the crux of a lot of Cassandra. Do you guys want to any more questions on the multi-data center stuff? Great. So, creating a table in SQL, it's, it looks the same. There's nothing special about this. The only thing to note, so you create a table, a bunch of columns, and you define a primary key. Now, that value there, because there's only one in there, that's actually the partition key of your data. This is really, really important to understand. You have what the partition key is essentially saying to you is that my data will have a natural affinity to a bunch of nodes in my cluster, and based on the replication factor you defined, it'll be across n number of nodes as you specified it. And what you're doing with the partition key is you assign a range of partition values to a node, and if your partition key falls into that range, that's the affinity to that node. And then Cassandra is quite smart. It will walk the ring to figure out where should I be placing the next replica of my data. And when it walks the ring, it looks at whatever you tell it to do, but it will look at, for instance, is this next node on my ring in the same rack my other node is in? Well, I don't want that. I'm going to put it in a different rack, because if I lose that rack, I'm more likely to lose my data. So you can get very, very powerful ways of placing your data in a very available fashion. But in this case here, it's a very simple. Your partition key is basically the same as your primary key. So the primary key, as it does in any database, it's uniquely identifying the row. A primary key in Cassandra consists of the first, when you create the table, the first column in there is your partition key, and then the remaining columns you specify there are your clustering columns. And what the clustering column is doing is once my data has now resided on a node, because of the partition key, I will use the clustering columns to give it a natural ordering within there. So this is quite important when you're looking at how you want the order of your data to be retrieved when you're pulling stuff back from Cassandra. And I'll go into some better examples on this.
Can we go a bit like in detail after the presentation, maybe in repartitioning in case of fault tolerance?
Cool. Yeah.
Yeah, it would be great to have.
Yeah. No, it's no problem. So when you create a composite primary key here, what we're saying is in this table here, I have a primary key that's the name of my team, and I've got my clustering columns are my player name. So everything here is being ordered by the player name. So if you're looking at retrieving a large amount of data on a wide row, it's important to understand what's the most efficient way I want that data to come back in an ordered way. So another thing to point out is you should never really do a select star from, but there is a limit. So Cassandra has, just to make, stop you doing stuff that's crazy, there is a limit that it will defaults to 10,000. This is if you do a really silly query that's going out to all of my nodes in my Cassandra cluster, it will stop at 10,000. You really should never be hitting this. If you model your data correctly and you query your data correctly, you should always be, this should never happen to you. So I just wanted to point it out. So here's an example of a very simple select where you're doing a select on the partition key. Really, if you notice, so if you look at the previous table definition, you see how everything's just ordered by the clustering column within there. There's that. So partition key is the team name, and then the player name is the clustering column. So it will have this natural ordering when the stuff comes back. Does that make sense? Yes, great. Here's a simple select. Very straightforward. Same thing with inserts. You can all understand this. This is really, really simple stuff. So ordering is an important thing to do. I mean, if there is a natural ordering to your data, try and get the clustering columns to do it for you when you create stuff. But if you haven't, you can use the order by to order things as you want. Only thing to point out is you can only do order by on columns that you've defined as your clustering column. Okay. If you do it on a column that you've not specified as your clustering column, it will not let you do that. Group by. Basically, you've done this. Your partition key is essentially what's grouping your data. Okay. Sorry, I'm going through this here. Go for it. Yeah.
Yeah, so about the ordering, does it fetch all the data and then do the ordering in memory afterwards, or can it do some multi-ordering?
It will. If you're talking about the client, is the client doing the ordering, or
if you change the ordering, like if you first make a query order by name and then order by timestamp, or
it will, yeah, as it'll be doing it on Cassandra. Yeah, it's more efficient to just have the natural ordering already defined. If you do say, if I've had to specify my natural ordering to be say by column ascending, and I do another query where I say ascending instead, that's not as efficient, and it will be doing stuff sorting for you.
Yeah, check.
Other thing to point out, difference with limitations to CQL is predicates. You can only do equality on your partition key. You can never do range queries or stuff like that, anything else. The clustering columns, you can do that. So what this means is when you start to get into quite rich queries, just be conscious that you will always need to specify the partition key. You cannot do range queries on your partition keys. Yep. Cool. So next thing you've got, another way of doing is a composite partition key. So a composite partition key, as you can see there, is where you basically make up your partition key of 2 columns. This is a very, very powerful thing, and this, when I go into the time series data, you'll see why this is quite important. But really what you're saying is, I'm taking 2 columns, I'm appending them, this is now the partition of my data, and this will determine where it resides. It's a very, very efficient way of structuring your data for when you're querying it, because you are getting a very, very, very precise you're going very, very close to your data on a single node. So it's very powerful. So performance considerations with CQL. As I said before, the best query is where you're basically going straight to your partition of your data, because what you're doing there is that when Cassandra gets that query, it goes, you're querying on partition X, it then chucks that over to the node that owns that X, and then that query is being executed on that node. So you're very, very close to your data. And this is essential to understand when you're in a system where you've got hundreds or thousands of nodes, because you really want to get the query executed very, very close to where the data is. Queries that span multiple partitions are naturally going to be very, very slow, because I have, if I have lots and lots of nodes, I have my data essentially striped across all those nodes. I will need to be jumping to lots and lots and lots of different nodes to get my range of data back. So they're just slow. Clustering columns are really, really efficient. Once you're got your partition of data and you're doing your queries on the clustering columns, it's really, really quick. I put this slide in here because I'd say it's a pet peeve of mine that out of the box authentication authorization is off, but it is there. Yeah, with Cassandra, you can create users, you can grant them the same stuff you get with any database. Select permissions, read, write permissions, everything. It is in there. Surprisingly, most people aren't aware of it, and by default, it's not even on. So it is there. If you need to be locking down access to your tables, you can do this. Please do it. It's always, I go into systems often where it's a production mission critical system and there's no authentication on connecting into it. That's never a good idea. But there's nothing you won't understand from doing this already from before. Another nice thing you'll find very, very handy to do when you're developing is query tracing. It's depending on how you're doing it. If you're going through this CQL CLI, you can essentially on your session you can say turn tracing on, turn tracing off. But what you're actually going to get back from there is a really rich, essentially a really rich trace of every step that Cassandra's taken to perform that query. It's very, very good to look at. Have I written a bad query? Am I written something that's jumping out to lots of nodes? It is your friend, tracing. You will get a lot of rich information, and I mean tuning this stuff is really important. And also it's quite educational as well. Executing these queries just from a playing around with stuff, you will understand a lot of what Cassandra's doing. It tells you which nodes I've gone to, how long it's taking. And by the way, this number here is not milliseconds, it's microseconds. So don't be worried. And a lot of it's done in parallel as well. So it's not just it's taking me this long, it's just giving you the indication of each step. So if you are looking at, why is my query running dog slow, this will tell you. And there's a very good blog article there, which I really recommend reading about it. Another thing you can do is TTLs. So fairly straightforward. You just specify a TTL when you insert the data, and that data will not necessarily be not quite deleted when the TTL is expired. It'll just no longer be returned. In the background, compaction will throw this data away for you. You've got all the standard data types you would expect. I'm not going to go into that. Interesting one here is one of the data types that was introduced recently is collections. Collections are, as the name suggests, you can have 3 different collection types on a column, and with CQL you've got set, lists, and maps. You simply The syntax is fairly straightforward. These were really introduced just to kind of make it a little bit easier for modeling one-to-many relationships when you're in this kind of very denormalized approach. But just be conscious of the performance of collections. You are basically serializing and the data back and forth. So this is not an answer to your prayers. You can't just put in everything in a collection. Yeah, it's new. There's lots of performance improvements coming out on it, but don't go crazy on it. It will be more efficient to denormalize your data further than going into a collection. But sometimes it's a really easy thing to use. And always favor sets over lists. Yeah, lists are not very performant. Great. Other thing you can do is counters. Counters are a way of just incrementing things in Cassandra, counters are a really interesting and somewhat controversial feature in the community. If you think about what you're trying to do with a counter, it's a distributed database. I have no locks. How am I going to get a consistent count across my database? And that's why you shouldn't be using counters if you require, your counters will always be accurate, but they may not be consistent at that specific point in time. I like counters. I use them a lot, and I've hammered the heck out of them with no problems. If I was doing something with money, I might be a little bit more cautious about using counters. But they're used in Angry. People use them a lot for analytics stuff as well. It's a very handy way of doing roll-ups of your data, so you can start using nicer ways of querying it. But just be conscious that it is an eventually consistent counter. And I will say there's a lot of work going on at the moment about improving counters in Cassandra, so it will be more and more accurate. Other thing you've got is lightweight transactions. So lightweight transactions introduced Cassandra 2. It's really a compare and set operation. It is not a transaction in what you would think if you'd come from, say, Postgres or Oracle. Yeah, all it is doing is it's really just simply going on a per statement basis, insert some records if it doesn't already exist, and if that statement fails, you'll get back an error to the client saying I couldn't do it. Similarly, within updates, it's all right, but don't go crazy with it.
How lightweight transactions cope with batch operations?
They don't at the moment. You can't do a batch statement with lightweight transactions in there. Batch statements are in themselves atomic if you're looking for atomicity, but if you're looking to using compared sets and batch statements, I don't think right now you can do that.
Okay, thank you.
But you're not the first person to ask for it, so I would watch that space. It's using Paxos to work out this consensus across your cluster. And I'm not going to go into Paxos. It's probably going to make you all fall asleep. But it is not as efficient. It is not. It has to go out to a multitude of nodes and get a consensus across those nodes as to can it actually honor what you're asking it to do. And because of that, it is not as efficient as you doing a standard read or a standard write based on that. So it's the classic use case for it. That the reason it was actually, I believe the reason it was introduced was somebody had this issue where I've got my Cassandra cluster spread across, multitude of data centers across the world, and people need to create a user account on their system, and they need to have a username. And you get that if I'm in Hong Kong and I create my account with Johnny123, and then at some time someone in San Francisco does Johnny123. How do I handle this? And this is a very common use case, and that's really what it's for. I'll say it again, don't go crazy with lightweight transactions. They are slower, but they're there when you need it. And this is an excellent presentation from the summit last year that you should probably have a look at this if you're interested in understanding why it's better to use eventual consistency when you can. Okay. Sorry, this is a very, very quick run through this. There's a lot more to hear, and by all means, grab me afterwards, ask me any questions you have, or in the Q&A. Yeah? So, data modeling in Cassandra. So, as
compared to SQL, would you advise users to go with SQL or any language-specific wrapper like PyCassa?
I mean, really, the question most people ask is, should I be using Thrift or SQL? Yeah. I mean, most people are using Thrift. SQL is quite new. Thrift is absolutely core to Cassandra. There's continuous performance improvements around Thrift. Don't feel obliged to not use Thrift if you're comfortable using Thrift. SQL is a hell of a lot easier to learn and pick up on than Thrift. If you've never had to deal with this before, if you've ever used a database, you'll understand this. It's pretty easy to pick up, so you're typically more productive. So from a engineering productivity point of view, I would always go for SQL. If you're looking at raw performance, which is quicker, that's somewhat debatable. There's different reasons why one might be quicker than the other. If you're looking at the native protocol into Cassandra so Thrift is an RPC based protocol when you're creating Cassandra. So you've got a client, connects, locks, takes that socket, does a reply, standard stuff. The native protocol in Cassandra is it's pooling a bunch of persistent connections between the client and Cassandra, and it's multiplexing requests over these sockets. So you'll get by default 128 concurrent requests being served over one socket between the client and Cassandra. And also, Cassandra uses this to push events back to the client to make it aware of a node is no longer available, you've changed the partitioning of your data, stuff like that. So if you look at it from a raw connectivity point of view, the native protocol wins. Then you start getting into the performance differences between the types of data you're looking to persist. And that's a really difficult answer. I've seen some people say SQL native outperforms Thrift 30-40%, and I've seen people say the complete opposite in Thrift. It really will come down to how efficient is your model, how efficient are your queries, the type of data and the type of hardware you're using, and the type of network you're on. I'll say from a personal point of view, I would never use Thrift again, just purely because I find this much more productive to do. And I've seen some very, very large systems now going down the SQL approach and the native approach. Does that kind of answer your question? So, as you know, Cassandra, it is not a relational database. It doesn't do the same. You can't do foreign keys. You can't do joins. So the approach to Cassandra is query-driven data modeling. And the first thing you need to be looking at with this is you have to start looking at what are the type of ways I want to query my data. And you really need to be looking at modeling your data around those queries. It's not you don't after the fact go in and say, oh, actually I need a index on this column. I've changed my query. I'll apply an index to it or stuff like that. You need to be very, very conscious of how I want to get my data. You need to be looking at what are your use cases? What is the data going to look like? What are you trying to retrieve? Do I need my data ordered? Am I nesting my data? Do I have to group it? Do I have to filter stuff out? Does my data expire? Do I need things retrieved back in chronological order? These things need to be thought through. It's a bit of a it's one of the things that I find a little bit less flexible with Cassandra is you do actually have to think about your model quite effectively, because it's always a challenge once you go live to change your mind and do things, and you want to reduce that. So just spend a little bit more time thinking about it. Denormalization is key to everything here. Everybody knows what denormalization is? Yes, great. So the advantage of denormalization is that there's going to be less seeks and less network traffic. And this is one of the reasons why you get very, very performance. And this is the same whether it's you've denormalized your data in an ordinary database or Cassandra. But the disadvantage is that you are duping your data. If you're creating a table for every way I want to query my data, you are duplicating it. And this is what I think people find very difficult to get used to, because we've all come from traditional database. Don't dupe your data. This is a bad thing to do. And the reason it's not so bad with Cassandra is just writes are very, very, very quick. Disks are very cheap, and it's also compressing to disk as well. So you should not out of the gate be worried that I shouldn't be duplicating my data. That shouldn't be the problem you're looking to solve. What you're trying to solve is, can I query my data very, very quickly? Can I get the throughput I want when I'm persisting my data? Don't get wrapped up in, you might need to if you're into terabytes or petabytes of data. This might be a consideration. But out the door, don't get wrapped up in duplicating your data. Also, avoid client-side joins if you can. So in this case, client-side join would be my app sits there, queries one of my data, gets back some stuff, queries another data. I mean, that's obviously going to be slower. And it does kind of negate a lot of the kind of power that you have with Cassandra for doing your stuff. You should ideally have a table that's optimized around that specific query. Don't try and avoid it if you can. There's situations where that's not going to fly, but really do try and avoid it. It has a very, it degrades performance, it degrades scalability. There's more I/O. It's just a very inefficient way of doing it. There is more quicker, more efficient ways of doing this than client-side joins. But I mean, if you have to, you have to. But don't start with that approach. Wait until you think you have a specific problem you need to solve, and that's the only way I can do it. Don't start like that. As I said before, I mean, don't be scared of writes in Cassandra. These are actually quite conservative in terms of the metrics you've got there. When you write to Cassandra, writing small tables is not going to be slow. The actual, I can go into it in the Dravadar a bit. It's entirely asynchronous. You can have async writes going on from your client to Cassandra. It's very, very efficient. If you're looking at, what's the kind of TPS I can get, it's usually a reasonable benchmark, 3,000 to 5,000 writes per second per core in a reasonably mixed workload environment. So if you've got an 8-core server, you're getting 30,000 writes second, possibly more. And in terms of response times, if you're seeing anything greater than a millisecond, there's probably something wrong, or disk or hardware or something else. The writes are super, super quick. And the reason they're quick is it's a log-based approach to writes. It just appends to the storage. I'm not going to go into it in too much detail, but it's just super quick. And it's also highly, highly optimized, not intentionally, but because of this approach to writing to disk. SSDs are your friend with Cassandra. It is exceptionally quick on SSDs, and it's very, very friendly to SSDs. You do not need to go and spend thousands on really super duper SSDs. Standard consumer grade SSDs, you're fine. I mean, it writes very, very quick. You'll see, in terms of, it's hard to say because a lot of organizations, they don't have the ability to plug in consumer grade SSDs. They have to go to it. But the cost benefit on SSDs Cassandra is very, very high. Really do go for it if you can. If you can't, you need to start looking at what's the most optimal disk configuration I have. What you guys did with commit log on an SSD and data on spinning initially is a fairly typical configuration. But think about disks. Performance. This is one of the reasons why I love Cassandra. It is the fastest there is for writes and reads. And this is not Datastax stuff. I mean, VLDB, that's a really good paper. They went and did a bunch of benchmarking on, I think it was Cassandra, HBase, I think Couchbase was in there as well. And it gives what Cassandra, it beats them for read writes, but it also gives you a very predictable scale with Cassandra. it does scale horizontally and in a very predictable fashion. There is no curve on your scale. It just goes on and on and on and on. And that Netflix blog there is definitely worth reading. They got massive throughput doing on that. The other one at the end there was another independent benchmark in terms of just the original VLDB one didn't have Mongo in there, so another one was done with Mongo, just again demonstrating lowest in latency, read-write mixed workload, stuff like that. The reason this is curved as opposed to straight is because the nodes are doubling each time. There is no curve. It's just like that. But so really the point I'm trying to get across to you is the reason you would be cautious about denormalizing is both storage and my writes. Am I going to be paying for this in some way? And the simple answer is no. It's very, very quick. Don't worry about it. When you have a problem, solve it. But to start, write to your heart's content. Any questions? Because this is very, very quick through this. Any questions now on anything you'd like to know about performance or hardware or anything like that? We can go into it later if you want. Sorry, did you? No. Okay. So, all I'm going to do now is go through a bunch of typical things you might have done in a relational world that you now might want to do in a Cassandra world. So, everyone knows what a one-to-many is. This is how you might choose to do this in Cassandra. Basically, the point is you're writing to two tables at once. Yep. And what you're doing is you're optimizing around reads. It's all about I will write to my tables and I will have my reads basically pre-optimized as a consequence. I think I don't really need to go into that. I think it's pretty reasonably straightforward. I mean, basically, I've got one table with a bunch of videos in there, and I've got another table where I want to look up videos by a username. And all I'm doing is I just got writing to both. One of them has my primary keys, my username and the video identifier. The other one just has the video identifier, and that's my one-to-many. I haven't in this, but the way you would there's really two approaches to that. Your client simply writes twice to both tables, or you wrap it up in a batch statement.
Thing is, in that case, when you have two sequential writes from the client, it's from the performance point of view, it's worse because the writes cost more than the sequential read or client-side join. You see?
No, writes in Cassandra are quicker than reads.
That explains. Okay.
Yeah. That's actually summarized the other point. That is the case. Writes are quicker than reads. It's a very, very efficient way of doing stuff. And there's a bunch of very, very good articles on it. So don't worry about it. Which I hate saying things like that, but do worry about it. But don't be too worried about it. A many-to-many. Everyone knows what a many-to-many is. Here you got a case where very stuff. Somebody posting comments on videos. Yep. So all you're doing here is I've got essentially two materialized views looking at either side of that relationship. This one here, my comments by my video, where this is my video identifier, the user who's posted it, and this is the other way, comments by user, and the video is pointed against. There's a one-to-many, and you're writing to both tables. Any questions on that?
So obviously the latter write operation can fail then once the first has succeeded. So is there any built-in best practices or any kind of built-in support for handling that kind of scenarios better? Or is it that you always have to just come up with some logic yourself so that you can survive from that scenario?
So are you asking, is there a way of making both those writes atomic?
Well, essentially, yeah, but I mean, obviously, I know there are no transactions, but
no, there's no transactions. You don't get anything for free. Yeah. So if that's an important point for you in terms of what your use case is, that those writes definitely have to be atomic. You would use a batch statement to do this, which are atomic. It's all or nothing. But batch statements come with a performance cost. They're not as efficient as you writing directly to both tables. So what most people would be doing in this case, if one of those writes failed, they'd have client-side logic to handle it. But you know, it's to give you an example. There are actually no, I can't give you that example. You have to handle it. If one of those writes fails, your client will need to handle it. Yeah, but it would be exceptional if your writes failed. It does scale up very, very high. I mean, Netflix, and we keep going on about Netflix, but Netflix have some very, very interesting benchmarks on up to, I think, a million writes a second in AWS doing this type of stuff, and no inconsistency problems. But it's not a transaction. It's not wrapped in a transaction. That's just how it is.
Yeah, I was mostly worried about the client crashing in between or something
like
that.
That would be a consideration as well. Yeah, you would have to handle it. There's no magic, unfortunately. But this is if that is, as I said, batch statements would be the way if you absolutely want atomicity on those two writes. But you will have a performance cost with that. So those are your choices. You either have something client-side handling this or that.
How big is that performance hit if you do a batch statement?
You're looking. It's more to do with how big would it be? To be honest, I haven't actually got a number on it, but you're looking at, I would say, 30-40%. Possibly more, depending on how big the batch statement is, and also depending on what the replication factor of your key space is going to be as well. But it's something to test and just see based on your data, the number of statements you're batching up, and the replication factor you're determining. But it is going to be more costly than a single write. Yep. All right. So the thing to what I mentioned it before is it's really important to understand the difference between what is your partition key and what is your primary key in Cassandra. Your partition key is, as I said before, it's really what's identifying. It's an MD5 or a murmur3 of something that gives you a big number that says my data is going to reside on this node. It has to be unique within your table. So if you insert a new record on that partition key, it will overwrite that data. Yeah. And it will just do it as an upsert. You won't get a violation on there. So you just have to be aware of that and just conscious of what you're doing, which I said there. So how do you avoid upserts is the problem. You need to think about some form of natural key or use a surrogate key for your row of data. Again, the risks with natural keys are, depending on the natural key, you could still fall into the case of doing upserts. Also, if you decide you want to change your approach to the natural keys, you've got a lot of data to then restructure, reinsert, redistribute it around your cluster. So why not use a sequence to generate a screen? You can't generate sequences in Cassandra. And if you think about that logically, another reason it's in there, because I get asked this question a lot, why don't you have sequences? It's a distributed database. How would I do sequences in a distributed database? It would have to be something akin to Paxos, which we know is not going to be as efficient, or I'd have to have some horrible lock across my database, which is going to defeat the purpose of using a highly available masterless database. So that's why you can't do counters. And I wouldn't even know how you would do them, to be brutally honest. So what you should look at is basically UUIDs. I said that before. So it requires a lock. It's going to kill your performance. So use a UUID. Everybody know what a UUID is? Great. So it's really just a big number that uniquely is randomly identified. You can have a timestamp component of it, or you can have a non-timestamp component. Just be conscious if you're going to start using timestamps for generating UUIDs. Again, not as performant as the version 4s. So But it's how much of a performance difference. It'll depend on what you're trying to do. If you're trying to squeeze out every bit, this might be important too. Indexing. So this is this is always an interesting point. So I'll just jump ahead to this. How are we for time? Okay, great. So you can create an index on a table in or a column family in Cassandra. Very simple. Create an index on a table and a column, just like that. And then you can go, yay, select star from my product table, where type is obviously the column I've applied the index to. But really avoid doing this, because if you think what this means, it's going to have to go out to the nodes and do essentially a kind of a scan of my data. So they're really not good for performance. I would never do one in production, just me. I might put an index on a column if I need something from a debug point of view or an operational point of view. It's an ad hoc type of query. I might do that, but I would avoid doing it on your tables. You're really, really much more efficient to roll your own indexes. Just write the data as you want to query it to the multitude of tables. Don't just drop an index on a table in Cassandra. That shouldn't be your default choice. It will cause you problems as you scale. It will cause you all sorts of problems. So avoid it. But I will say, it's obviously a very popular feature in Cassandra. I mean, it's very, very handy to do. There are lots of improvements going on in Cassandra to make it more efficient. So it will get better, but it will never ever be as quick as you doing a query based on a partition key of your data. It will never be as quick as that. So just be cautious with them.
So, is there any performance implication when you do writes on a table where you have secondary indexes?
That's a good question. I'm not sure actually. I would have to say yes, because it's doing more work, but I'm not sure how much of a performance impact it would be. It's also it's almost certainly going to be parallelizing it. So it's whether what's the performance? Are you looking at load, or are you looking at perceived response times on performance? I've never had someone clearly say to me, I have a performance problem, writes to a table based on there being an index applied to it. But logically it's doing more, so it's going to have some performance impact, but I actually don't know. But because I never use them. But I mean, on the flip side, another way of thinking about this is what would make this more efficient. Yeah. Well, obviously, if I wasn't doing a select star from a table with this, if I was actually going select star from product where my partition key is X, and then I'm doing a scan, so at least my query is being isolated to that one node that I'm executing against. So there are ways of making it more performant, but just really be cautious about them. But there are going to be improvements on it. So what I'm going to do now is just really go through a bunch of kind of typical roll your own indexes approaches to there. This is an example of a keyword index. All you've got here is you've got somebody who wants to be able to tag videos as based on a keyword, not dissimilar to, I think, your categorization piece. You simply, I've created this, here's essentially my videos table. The other one at the other side, I've just created basically my tag is my partition key. So when I'm executing my query saying select star from video tag index where tag is equal to action, you'll be able to then get back your data in a very efficient way. So that's that's one approach to keyword index. Partial word indexes, very similar stuff. It's all about the partition key and my data. So then you can basically drill into it. I don't think there's anything particularly complicated about that. It's just if I want to be able to, for instance, do a select based on a domain of an email address, this would be a way of breaking down what is my email address and inserting it using the bits that I want to be querying by. So partition key, clustering column, and then away you go. This is one of my favorites, bitmap indexes. Bitmap is not a bitmap index. It's a bad name for it, but it's kind of come out as that. This is a really nice way of really loading up your data in a way that it's very, very optimized for reads. It is not a bitmap index, as you would say. So a way to look at this. It's a good example here. I have a car park, and I want to find in my car park various types of way of querying my data. So what I do is I've got a bit of a truth table here. So all the various combinations I've got of querying my data, color, model, color, make color, make model. But you basically are looking at inserting a row for each permutation of the data. Now, obviously, the more you have this way, the more amount of data you're going to have to insert. So, how would we do this? In this case, based on there, I've got my car location index. I have a composite partition key, which is the make, model, and color, and then a clustering on the vehicle I do. Fairly straightforward. So, do you understand what I mean by the composite partition key? Yeah? Cool. And then, when I want to insert, I basically pre-optimize it, and I insert for each one of those a piece of data for every single permutation of that. And now, obviously, if storage is your problem, this is probably not a good approach to take. Or if you have lots and lots and lots and lots of kind of, what's the word? Lots and lots of different values as to how you might want to do this. But what it is really doing for you is it's a very, very quick way of subsequently reading back your data with a pretty dynamic way of querying it as well. So I do like these. So what I can do now is I can basically go, I want to find all blue Fords, or I want to find all blue cars. It's very, very quick. It's as quick as you could, because you're going on the partition key, it's very, very quick. But note, you're saying empty, empty value. So you've actually created one of your rows has that as the composite partition key. Yeah. 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 It has. I just like it because really what it's actually quite. I have actually seen it used. It's really, really quick when you have a very rather than doing lots of predicates on your data. This is as quick as you can get with reads in Cassandra. You're going right down to the partition key, and you're getting your data back straight away. Very, very efficient. But the reason I like to show it is because it's this whole thing about writes. Don't be worried about writes right away. But to a certain degree, because as this does get wider, you're going to have, you don't want to end up with thousands of writes for every single one you want to do. But very, very 3 is okay. I've seen it done up to 5. When it starts to get beyond 5, I'd start to go, really? Do you really need it like that? I haven't gone through. There's tons of stuff on other ways of rolling your own indexes, various approaches to look at. One of the chaps, Patrick McFadden, I'd suggest Googling him. He has lots and lots of very cool examples of other tricks to pre-optimize my indexes. Any questions on that? Yeah? Great. So, this is a use case for a very, very popular use case for Cassandra. And it's really, it's probably one of the best, based on the way the storage works in Cassandra. It's really a very, very good use case for using Cassandra. So what do we mean by time series data? Sensor data, historical data, all of these type of use cases. It's when you've got lots and lots and lots and lots and lots of samples of data, and you want to just grow that row out as your data grows. Cassandra is great at this. You'd almost say what it's made for. So and it's because it's using essentially a big table. What you've got is one partition of my data, and then for every single sample of my data, I'm just growing out like this as I get there. So obviously, your approach to how you partition your data is going to be important, and the ordering of this is going to be important as well. So if you, depending on how you want your stuff to come back, you should be conscious of this. And I'll show you some examples. And I've got your question around fitting it all on one node. There's an approach for that as well. So this is like the standard example for time series data, weather data. You basically got clustering column, partition of your data on a weather station ID. Every sample of my data, I'll grow out that way. So, this is the weather station identifier is ensuring that my query is going to be run on that node that owns that partition of data. I can then quite nicely do predicates on date ranges, for example, stuff like that, and get my data back. Stop me if you have any questions on this. So here's creating a table for this, storing temperature on there. That's fairly straightforward. You've got main thing, partitioning, clustering column. Yeah, this is where my data will reside, and this is basically the order of my data as it's going to be on disk. So when I'm reading it, it's a very it'll make it more efficient, and also you can do range queries and stuff on it. Very simple to insert, very simple to query. Everybody read that? So partitioning is really the key with sensor data. First thing you got to remember is all of your data will have to fit on one node, because if you have a massive amount of data and if it doesn't all fit on that one node, what are you going to do? Because you've basically defined a partition of my data that means it's all going to fit on that one node. If it doesn't fit, what do you do? This is where composite partition keys come into play. This gives you the ability to break things up further into more granularity around your data, how it's being persisted. And usually, a very common case is to drop a date in there as well. If I want to make sure that my sensor data or my time series data is nicely evenly distributed around my cluster. So the reason there's two reasons you want to do that: physically fitting it, but also hotspots. You want to avoid having my data, every query for this particular data always hitting the same node, because it's particularly with time stuff, because if you're doing time-based queries based on 7 days ago or something like that, so I want to know what every day I want to look at something that was 7 days ago. For that one day, all of your data will be hitting that node. So think very carefully about just essentially getting it more and more distributed around your cluster. But composite partition keys are your friend in this. Same thing with reading and writing. It's very, very straightforward to do. I don't think I have to explain that. Cool. So ordering is another thing. So this is quite handy, where you want to, for example, you want to read say you wanted to be chucking away any sensor data that's older than X period of time. You're going to use the TTLs to do this, but you always want to get the most recent bunch of samples of that data. So here, obviously, you got the same as before. You got weather station ID and date as your partitioning data, but here I've specified the clustering order by to be event time descending. So this will basically mean when I go into my row of data and I'm going to get the earliest first, and I will just go down that way, and the TTL in Cassandra will be chucking away the older data as it comes through. And this is a very efficient way of doing it. But if this was not Cassandra, you would have to be having some horrible batch job going in periodically, deleting your data, tidying things up for you. It will just do this. So, but ordering is really important, particularly with sensor data. Try your best to get the data back or have it naturally ordered in the way you want it back. Because when you get to a level where you're getting, billions of samples, billions, millions, lots and lots of samples of data, you don't want to be taking this into in-app. You don't want to be ordering it how you want it, and you want the data to be naturally ordered in that way on disk. So it just gets, because Cassandra is going to be streaming that data across to you as the order it comes through on disk. So it's very, very efficient if you optimize the ordering around how you want to use it.
Okay, so you're going into the TTL.
So, here, for example, I'm inserting to that table using a TTL of 20 seconds. So automatically is a bad word. Your data will appear to be deleted after 20 seconds, and eventually, once all compaction and cleaning up happens, that data will disappear. But it's very, very simple to query. I don't know if that was what you were asking.
So you gave the argument that if you didn't have the TTL in any other system, you would have a batch operation every certain interval in time interval. Do the TTL expiration checks happen in a batch operation or during read time?
Both, actually. So if you got back data that was TTL'd, it would be thrown away. And then you also have essentially a background process continuously running that purges it from disk. So, and TTLs are, you don't get nothing for free. TTLing lots of data. There are obviously going to have to be stuff tidying up after you, and this is where you get into the level of tuning, looking at the type of disk I'm on, the type of compaction strategy I want to use, controlling the thread number of threads you allocate to compaction. Do I want multi-threaded compaction? Things like that. There's lots of ways of tuning this around the workload that's happening on your system. And if it's all just writes and you're throwing the data away, then you can do certain things if it's mixed. And you can even do cool things like pinning certain column families to solid state disks as opposed to spinning disks. So you can get very, very fine grained on the tuning, and as a consequence, the compaction strategy that's happening there. They're looking at it now. There's people actually, I think they're starting developing a specific compaction strategy optimized around time series data as well being developed to make it even more efficient, because it's not naturally the same type of data that you would be using in just standard static kind of structures. So it's continuously being improved. And I'm actually really looking forward to that new compaction strategy, because it will make a big difference. So this should always be a consideration with sensor data. How do you mitigate spikes? So this has happened. eBay have a very interesting blog on this. Great, I'm capturing every time someone posts a bid. I have some fantastic auction that everybody starts bidding on. I've hit that ceiling of what I can physically accommodate on my node. And really your approach to this is to use, essentially introduce a workaround to basically split your data across nodes. So have this bucket ID. And it's not something to... way I've seen people do this is they have it in there, but they have it set to be, say, 0. When they start to see a problem with this, they update their client code to essentially start generating a random number between, say, 0 and 4. And what this will mean is your data will essentially then be striped across those 4 nodes. You don't want to do this out of the box, and the reason you don't... Sorry, before I go on, does that actually click? Does that make sense what we're doing there? So the reason you don't want to do this is it's going to be obviously more expensive to read, because you're naturally going to have to go out to all of the nodes, pull them all in, and also if ordering is important, your ordering is not going to be naturally ordered because I've pulled my data in from a bunch of nodes. So it's much more expensive to read. You have to iterate through the numbers. You have to go out to each node and get them back in there. So it's an option for you, but it's not something fantastically magical that's going to do it. It will come at a cost to do it. But just if you have that variable nature of your sensor data, The worst thing that could happen would be in production, all of a sudden you fill up a node. So just think about it. If you're in for instance, if it's a time sample basis, if it's every 10 seconds, you have a fairly known number of samples you're going to be getting. If it's, I don't know what else it could be, but if it's something else that's quite variable, there are options to mitigate that. So as I said, only do this as a last resort. Basically your read performance will degrade when you do this. Okay. How are we for time? Okay. I put in way too much in my slides. I've been talking for ages. Are you guys interested in a little walkthrough on the native Java driver? Yeah. All right. So I kind of spoke a little bit about the native protocol before. When you're using the native drivers in Cassandra, you're utilizing Cassandra's native protocol. And what basically the driver uses Netty to do non-blocking I/O on reads and writes to Cassandra. So what you get is a completely asynchronous architecture around how my clients are connecting up, and also internally how Cassandra is doing stuff is quite cool as well. So what you're able to do is basically submit multiple queries at the same time via the driver to Cassandra, and then it will dispatch the responses based on essentially the appropriate client thread that's sitting there waiting for it. So this is the reason. This is actually primarily why you get the performance improvements around the native driver, because it is basically asynchronous and non-blocking under the hood. It may look like it when you use it, and you can choose whether to execute queries in an async fashion or a sync fashion when you're using the driver. But it really fits. It really fits well into Scala. It's really nice around that. Other thing you can do with the native drivers is there's lots of very efficient load balancing policies within the driver that will, you can configure your client can basically be given awareness of the partitioning of your data in your Cassandra cluster. So it can know to say, rather than I just drop to any random coordinator in my cluster, I'll naturally go to the node that owns that partition of my data. So my query is, my coordinator's chosen to that, and my data is running on that. So it's a very, very cool thing to do. There's also stuff around latency awareness, because if you enable it to do this, you basically can have feedback from Cassandra to your client saying, well, this node's kind of not feeling too good at the moment. Let's not use it. You're getting more efficient queries around there. There's a lot on this, but you can also have stuff around configuring the consistency policy. Does everybody know what? Because I haven't gone into consistency in Cassandra. Do you know what we mean by consistency? So you can basically drop automatically down from a strong consistency to a weak consistency. So, for example, you've got a query where you're saying, I want super strong consistency. I want to go across to every single virtual data center or replication group I have, and I want an answer from all of those to make sure my data's consistency. All of a sudden, one of these data centers blows up. What do? You either, if you don't do this, you would fail. Your client is saying strong consistency, and that can't no longer be honored because that data center is blown up. And there's basically ways you can tell the driver to say, okay, now drop down to a slightly, say, local quorum, where I'm only concerned about the consistency in my data center, in such a way that when that other data center comes back, the data will then be repaired and replicated across. Does that make? I should have probably drawn a picture for that, but again, lots of stuff on tracing in there. Also reconnection policies as well. If it loses connectivity, a lot of the typical stuff you get in most kind of connection pooling type stuff. But really an important thing to really just get across is the synchronous or asynchronous nature of making your calls. It's what makes it very, very quick. Excuse me. We have a bunch of drivers. I'm not even sure if there might be more up there. You got Python, C++, Java, C#. There's continuously stuff being. I think somebody's working on the Ruby or the Perl one at the moment. They're all up there. Have a look that URL to download them. As with all this stuff, it's in Maven. You can just add that to your POM, and away you go. Documentation's there. API documentation's there. So when you want Cassandra, when you want to use the native protocol, you do have to make sure Cassandra is configured to use it. Make sure in your Cassandra YAML file you put start native transport to be true, hence it will be up and running. I've gone on about how amazingly efficient it is. Standard mappings between the SQL3 data types and the Java data types. So in a syntax fashion, the Java driver is really using they're using fluid interfaces. They like this chained way of constructing and querying your data, and that's what it's been built around. First thing you'd want to do is, and this is really, I'm shooting through this, there is a lot of more detail around this, but first thing you want to do is in your Java code, you'd essentially instantiate a cluster, and I'd say, using a builder pattern, cluster builder, add these contact points, and these are basically they're not single points of failure, they're essentially points of discovery in your cluster. So it will go up, connect to that cluster, discover everything it needs to know about that cluster, and it's now basically registered the client between itself and Cassandra, and they're now starting to speak to each other. It's worth making sure you pass in more than one address to connect to, because if that address at that point in time is not available, it won't be able to discover your cluster. And just as you would with JDBC, you want to tidy up after you're done. Next thing you'd want to do is connect to a key space. So I'd basically be creating a session on that cluster. Optionally specifying the key space, you can just connect up and make your queries in between the key space if you want. You just basically call connect on that key space. It gives you back a session object. Again, make sure to tidy up after you. This should be very familiar to anybody who's ever written DAOs. You basically call execute, or in this case it would be execute. You could execute async if you wanted to. There's an insert statement in there. Yeah. Reading data. Very, very similar. You get back a result set, you iterate through that result set, you get your data out. Again, session execute, that could be synchronous or asynchronous. You've also got prepared statements as well. You basically create your prepared statement object, you create a bounded statement off that statement, and you start binding the dynamic values to that. Again, the advantage of, just like JDBC, prepared statements are pre-compiled when they're executing it, so you don't get that overhead of the CQL being interpreted. But I'm a little bit confused on this one myself, but there are performance improvements being made around prepared statements. I think it's generally to do with the distribution of the compiled CQL around the cluster. But it is it's very, very efficient, but they're making it more efficient for you. You also have the ability to essentially programmatically build queries using basically the builder pattern. You create query builder, insert into values, blah, 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 and then you call execute on that. Fairly easy to read. Any questions on that? Consistency. Same thing you can do is when you do your, for instance here in your insert, you just call, I want a consistency level of all. This doesn't have to be all. It could be 1, 2, quorum, local quorum, however you choose to say. But really the point is you're setting the consistency level. The client is responsible for setting the consistency level at that individual query it's doing. You decide per query what level of consistency I want in my data. And this is one of the strengths of Cassandra, is it's this tunable consistency. You can decide. If you're happy with weak consistency, go for weak. If you want strong, go for strong. You decide what you want. But just be conscious that, if you think about it, when I'm saying, if I say I had a consistency level of, does everyone, okay, I'll say it anyway. Say I had a consistency level of 1 with a replication factor of 3 on my key space. So all I'm saying there is my client connects up, executes a statement, and I've got replication factor of 3. As soon as one of those nodes comes back, it's no longer, it goes in its merry way. It's not that these other two writes are not going to happen. It's just as soon as one is act, it's happy, it's on its merry way. Cassandra will continue to get your data consistent. So if you go for a stronger consistency, say you went for 2, you're going to be sitting there waiting for 2 of those nodes to act. And then the consistency gets stronger and stronger as you go up. You can go to a level of local quorum, which is basically a kind of a fault-tolerant way of having a consistency level where you can handle n number of nodes being unavailable, but still have a very strong, reasonably strong level of consistency in a local data center. You can then have quorum across all of your virtual data centers, or then you can have basically every single node that data has been replicated to will have to give me an ACK back. But you decide what you want, but just be conscious that it's not Cassandra, the database, that's is going to be doing more or less. It's really what you're blocking your client on, what you want it to basically give up on and say, fine, I'm happy, I've done it. Does that make sense? Cool. Tracing, as I said before, you can enable tracing on a per query basis. This will help you when you're developing, will help you when you're debugging. You do not want to have this on in production unless you need it, because it is doing extra work when you have tracing on. So really fairly straightforward. You just basically do .enable tracing on that query. And when you want to get it back off your result set, you just get the execution info. Off that, you get this nice query trace object, which will basically go in and give you back a very, very rich amount of data of everything that's happened as Cassandra was executing that query. And it's for parsing, preparing, determining my replicas, sending a message to this node, that node, acquiring all the different stuff, appending to the commit log. So when you're looking at why is my stuff not performing, you're going to be looking at stuff on Cassandra or what the perceived performance of the clients are, and this is where you want to look at a bit of both. But it's really handy to do this. I've seen people sometimes do this on a kind of a sampling basis, so they'll have 1 out of 100 queries, they'll turn it on and they'll log that out. That's one approach, but it is more costly to do tracing. It is doing it, so just be aware of it. I find this really helpful for me. You will learn. Sorry, go ahead.
So can I enable this the query-specific tracing without having to edit and recompile source code?
No, it's programmatically done.
Okay.
Yeah.
All right.
Saying that, I am actually writing something to let you do it through configuration. There are I think because I'm finished on the Java driver bit, there are depending on what you're used to, depending on what you like, or depending on your environment operationally, how do I manage configuration? How do I tune things at a client side? There's drawbacks to having a fluid builder pattern for building your queries up because you are programmatically doing it, and there are a massive amount of tuning parameters you can do on the Java driver. It's very, very tunable, and it can be quite a challenge to build up that level of tuning programmatically. You're having to essentially go do it like this, do it like this. So I'm actually writing something right now. I'll hopefully have it open sourced. I don't know when soon. Be on GitHub. And yeah, the goal with that one is to essentially very much give me a session back, and then externalize all the configuration of that session to other property files, JNDI lookups, things like that, because it can be it depends what you like. It depends what your environment is like. But I have a lot of people where that's not, for instance, the connecting up to 2 endpoints in code, specifying that programmatically, it might not be a great thing to do. So all the kind of IOC stuff with Spring and wiring things together and stuff like that, it's I'll hopefully have something out soon, which will make it a little bit easier just to extrapolate that. And I think one of the things is going to be query tracing. How do I go into a production environment, turn on my tracing, turn it off, get back a sample of my data? But the slight difficulties with it, because a lot of this information is it's immutable when you instantiate things. It's not the query tracing one, because that is per query, but a lot of the configuration around the cluster is, once you've instantiated that cluster, it is immutable. So yeah, going off on a tangent, but it's in there. I'll just point out Op Center to you guys. Worth having a look at. It's free. You can download it. It's a very handy GUI tool for managing your Cassandra clusters. You get richer functionality in it when you're managing a Datastax enterprise cluster. For example, we have repairs. Yeah, one of the things you have to do with Cassandra is do a repair of your data within the GC grace period to make sure you're continuously repairing your data, because it's an eventually consistent database, and it will do this for you in the background. You do no longer have to do repairs. Other things coming, you can see on it. I'm not a sales guy, so you'll see stuff around performance optimization, tuning, alerting, backups, all that kind of stuff. But it works fine with Apache and Community Edition, and you just get extra stuff with Datastax Enterprise. Other thing to point out: if you don't like GUIs, which if I'm need to hook into something else, everything in there is exposed as HTTP APIs. So if you need to be you have to be using Nagios or whatever you want to use the APIs, it is there as an API for you to use as well. But I'd strongly suggest have a look at it. It's continuously improving. It's one of the things that we're investing in a lot of engineering in Op Center, because I think when you get to hundreds or thousands of nodes, it's very difficult to manage those in an efficient way. So things like bulk configuration, you can use Chef and you can use Puppet and all those things, but there's nice GUIs to let administrators go in there and change things. And also lots of the standard operational stuff you want. But do have a look and play around it. Also, Datastax Enterprise is completely free to download, use in production. Sorry, not say that again. Free to download and use in development and testing. You only pay for it when you go into production, and it's very good value. The other thing to think about, we have a startup program as well. So if you go to our datastax.com, if you're a startup, you can get it for free if you want it in production. And I think there are conditions around it. I think it's based on revenue and stuff like that. But you go in and you apply to be part of the startup program, and you get to use Datastax Enterprise completely for free. So yeah, I think there you go. That's me. I'm done. Any questions? Damn. For Datastax Enterprise. It's per core or per node. It will depend on. It's subscription based, so it's an annual subscription, and it's there's three kind of levels of subscription. You've got just Cassandra, you've got Cassandra and Search, and Cassandra Search and Analytics, and it's an annual subscription. Yeah.
So it's not limited to physical core.
It's physical cores.
It's physical.
Yes. Offhand, I don't know, but there is a appropriate licensing model for AWS. I mean, just so you know, most of our customers are on AWS.
Okay. I'm pretty sure we have a lot of questions, but we should let Johnny take a break also.
I don't mind. It's all right.
You don't mind?
Let's go for it. Yeah.
You don't want cake? Are you sure?
I've got water. It's all I need.
Cake,
My body's a temple.
Just a quick one. Will you put these slides online somewhere? Will you put these slides online?
Sure, yeah.
Thanks.
I can publish.
Cool.
2 short questions. When we restarted Cassandra, we had sometimes cache corruption, which was quite weird. And when we backed up the S tables and tried to restore them, we sometimes got S table corruption as well.
Well, so SS table corruption's pretty bad.
Yep.
That's not something you want to have.
Nope.
You can scrub. There's all the tools to tidy up you try and repair those corrupt SS tables. But
if only one is corrupt, it's not a big deal. Just clean out everything, and it will replicate everything from the other nodes.
Yep.
But I was wondering if there's some other underlying reason why this is happening.
No, there shouldn't. I mean, there's no. Typically, it's either going to be a bug in Cassandra. Which version of Cassandra are you on?
I think 1.6, 1.7.
Yeah. I'm trying to think. Is there anything I know? 1.26, 1.27. There's nothing outstanding in my mind as to why that specific version might have corruption issues. If you're looking for stability in issues, I mean, there are varying degrees of stability with the Apache, the community releases. Always to have a look at the version that's bundled in with Datastax Enterprise. If you're not using DSC, try and go for that version, because we have tested it and we think it's stable enough that we can commercially support it. So, and you're also going to benefit from that. As to why you'd be getting corrupt SS tables, there could be a variety of reasons for that. It's difficult to say. I usually start with, is it something to do with time? Have any form of drift on what I'm doing? Is it I've got corrupt storage? Are you making are you making lots of runtime schema changes? Nope. Yeah. It's a whole can of worms. You'd have to look at, but you shouldn't be getting corruption, and corruption is not a natural part of Cassandra. So it's got to be it's either a bug or something in how you're doing it, or something how you're doing your snapshots. But there's no magic for doing snapshots that would stop them. It's a very, very simple thing. It just does it. Turns a soft link into a hard link. I will say when I have seen I've seen corruption in Thrift more often than I have seen it in CQL, and I'm not quite sure why. So yeah, I'm just saying as an observation. I don't know why, but I have seen it. But that might also just be more to do with the number of people using Thrift versus CQL. But no, there's if the SS table, it's an immutable file on disk.
So it should be easy to just push on S3 and then get it back and restore.
Yeah. So there's nothing weird about it.
Okay, thanks.
Sorry for the next question, but what to deal with when you need to repartition your data? You have stored them in 10 tables, and you realize that your model is not optimal. Yep.
You have to go and basically remodel it and restream the data back in. There's a bunch of approaches to do that. If it'll depend on, are you doing this in production or are you doing it as part of development? You should be looking at the SS table load of stuff, turning SS tables into potentially JSON, transforming them at that level, and then turning them back into SS tables to then stream back in. There's the other approach to do is to just start writing twice, and once you catch up, if you're TTLing, you'll eventually get there. But there is no magic bullet or tool to do this. There are, the one I'm seeing looking quite good is Pentaho Kettle. It's a very nice ETL tool that hooks in pretty efficiently into Cassandra. But yeah, there's no special way. Basically, you're looking at SS tables or just writing the data again, pulling it out, iterating through it, or writing it back in. It's one or the other. Most people would be. It'll come down to is my data TTL'd? So you can just start and then eventually catch up. How much data am I having to do this for? If you're into petabytes of data, this is going to be an expensive operation to do. You will literally have to take the data out, try and and do the transformation like that. And this isn't a plug, but one of the with DSC, the DSC Analytics is basically a HDFS compliant file system that sits on top of your Cassandra column families. So you can run Hive queries that could read in your data, do joins across your column families, and then write it back to your new column family. We see people using that for that, but that's part of DSC. It's not part of Cassandra. I have to say, I think Pentaho Kettle. It's free. I believe it's open source. It's actually not bad, but give that a go. I typically use I would typically go for the SS tables myself to start with. But you've always then in this problem of catching up. At what point do I do it? So I have to snapshot right to both tables, take the old SS table, start streaming them back in to the new column family. So you need to think carefully about doing it and when you do it.
Just let me interrupt before we go to next questions. Datastax actually gave some mugs.
Hey.
There's like half a dozen of them. So there's no democratic way to do this. So I will just go and give 2 to the presenters. And because I did take that part, and the rest, either you can assign or you can make them fight for them.
Fight for the mugs.
Well, there's like 6 left. So you can go based on the questions or something like that.
I'll start throwing the mugs to people.
Can do. We need to clean after, but it's okay.
One question is like, if we do some analytical on top of Cassandra, because now it's like there's Hive and then the other one is like big.
Yep.
So which one actually much more efficient or?
So you're talking about in general analytics across Cassandra?
Some group by or whatever.
I like Hive myself. It's really easy to use. I think I would just use whatever you're comfortable with, really. The problem's going to be how are you actually running this against Cassandra. So if you wanted to be using the DSC analytics piece, is that what you're asking about? So that's a HDFS compliant file system. So you can run MapReduce jobs, you can run a Hive, you can run Pig. I think you can run Mahout as well, all against your Cassandra column families. So that gets used for analytics. And some cool stuff coming out this year as well. So watch that space. I can't say anything else. There's some very, very cool stuff coming out.
Sorry. Yeah, a question in between.
You get a mug.
Congratulations. Yeah.
5 more questions.
I'm not taking one. So about hooking into writes. So we're using Elasticsearch and Cassandra. Do you have any plans on providing hooks on all operations that we can index the data we're writing to the database?
We do. I mean, we do this.
Have hooks?
We do this right now. Possibly our marketing needs improving. So one of the. So do you mean community or do you mean?
No, community.
I mean, you got Solandra out there, but it's a really difficult thing to solve. This, and the reason, because it's difficult to solve, it's part of our enterprise product because we've done a lot of proprietary changes to Solar and how Cassandra hooks in and regenerates Lucene indexes based off your column families. So, yeah, I'm not aware of anything particularly magical in the community side that would do this. But if you're into that point, I would strongly suggest you should look at DSC search to do this.
I was wondering how that's implemented, but apparently it's a hook and a Solar index.
Yeah, it's very straightforward. What it does is you write to your column family in Cassandra. There's an asynchronous Lucene index built off that column family. Sitting on top of there, you've got Solar, and then you've got however you choose to do your Lucene indexing and everything that Solar gives you on top of that.
Yeah, sounds nice.
Yeah, that's what it's there for. It's actually pretty popular. I think the reason it's popular is a lot of people come at it from I could do this in a RDBMS world. I'd like to be able to do averages and counts and stuff like that on my columns, and you get all this. You basically got a search engine sitting on top of your Cassandra.
So basically, we have hear 8 different questions about time series databases.
I've only got. You only get one mug.
But I've ordered them from like the order from the least specific to like slightly more specialized. So if and when they get too uninteresting, then perhaps I should be stopped and we could speak later about those more specific questions, right?
Go for it.
So basically, as a background, we are evaluating Cassandra as a solution for our problem, which is a time series database, and so something like let's say 1 million rows, and in each of it like from 10 to 100 millions of columns by timestamps, and basically these are all sensor measurements, and for each sensor we keep perhaps like 20 to 50 like a key value store of like 20 to 50 different columns, but these are not always the same, and not every data point contains the same columns, and they are picked from, say, a range of like 500 different options, right?
Yeah.
So the first question is how the best way to keep this data would be, like to keep like a map in the column, or do some custom serialization, or.
So, if what I think you're saying is you want to have you want to have time series data where each sample I'm having a different sample of data that might not be there for the next sample. Is that what you're saying, or?
Yeah, and every timestamp is like a group of data with like 20 or 50 values.
Okay.
With like different keys.
All right, I would probably use a set.
A set. Okay.
Yeah. And you can store. If you start to get into the hundreds on sets, I would be a little bit worried. But if you want to do basically a sample, some key value of that sample, some key value, let's do it like that.
Okay. So you said earlier that serialization is a bit expensive.
It is, yeah.
If we were to optimize serialization manually to our needs, would this be an option to store like a binary blob or something?
Yeah, just blobs.
Okay, so this is something that is commonly done.
Difficult to say. There's nothing specifically weird about it. People store blobs in Cassandra all the time. So, but yeah, if you want to do that, yeah, I do a blob.
Okay, thanks. So we have when reading, we have a bias towards, say, the last 10k or 100k records. So the last 10k or 100k columns, and I was interested in whether it would cause like a hotspot or something. So,
are you talking about how
data is being read out? Like we are mostly like in 90% of times we're querying like the last 10 to 100k or to 1 million columns, and the first half of data will not get queried as often.
I don't understand. That's very difficult to understand what you're saying there.
So basically, perhaps. Okay, let's imagine this that we are inserting like say 10 records per second for like a year.
Yeah.
And we mostly query like the last month. It's not exactly the same, but I was interested if such a pattern where like recent stuff is queried more often would introduce like a hotspot.
No, but you'd want to be using the clustering order by on the most recent first.
Okay, so a cluster based on like the period of time or like the amount of records. Okay.
If it's date and time, it's either going to be ascending or descending. So choose if you're only carrying, if you're querying it based on, the month's worth, you want that data to be naturally like that. So look at the clustering, the order by on the clustering columns to do that.
Okay, all right, thanks. So mostly the data is being inserted as it comes in, like based on timestamps, but there are some rather rare cases where there is a bunch of data being inserted afterwards. Will this cause a problem?
So
we are basically inserting the data with a current timestamp all the time, but there will be cases where some data is being inserted like in between later.
Between.
Yeah.
That's a really good question, to be honest. I'm not sure. I think it from a read point of view, it shouldn't, because once it's written to disk, it's written in the right order. So, but I'm wondering if the compaction might cause a slight when you actually essentially flush the mem table to an SS table, it might be doing something funky there. But it shouldn't make much of a difference. No.
Okay,
But
all right.
it's a really interesting question. I would explore that. Just trying to understand is there I don't know, to be honest, but it shouldn't, because once the SS tables are written to disk, they're written in the order that's in there, and that SS table is immutable. That's what makes it very efficient. So the fact that you've gone in and changed the column family, it means the data is now like that and being flushed to disk like that. The problem you might find is if your column data is split across a multitude of SS tables, and you need to then start thinking that in itself is a bad thing. You need to look at ways of making sure I'm not having to my column family isn't split, because if it's split across more SS tables, then you're going to start seeing performance impacts around how the Bloom filtering works to say, well, which SS table does my data reside in? That's the bit that you'd want to experiment. But I don't think interjecting jumping in at the point is really going to make that much of a difference.
Okay, but what about case where this should happen irregularly often? Like if there's like an anomaly where some road this happens like awfully lot, would that cause a problem? If it does not happen only once, but like 1,000 times or 100,000 times?
You'd have to test it and see.
Okay, all right.
It's something you'd really want to test that. The thing to also make sure when you test this, you're testing it under a representative workload, because what's going to cause you those bottlenecks, I think, would be compaction. That's what's going to be it. So just you'll want to be looking at tuning this and trying it, but you will have to test it and see.
Okay, thanks. So now. Okay, all right.
You can come grab me afterwards.
Okay, I'll do that. Thanks. Yeah, that's what I said about like let's stop him if it gets too specific. Yeah.
Here's a mug for you, because.
Yeah, of course. That's what I meant.
We need to get some stickers and T-shirts.
Thank you. So okay, we have some more complicated stuff now. Actually, this might have been answered before. Like when you spoke that there is no magic bullet, but perhaps sometimes we would create like an index or like a separate table based on like some representation points. Like we take one row and like we filter it down to some single row for like later. For like querying it more efficient later.
Yep.
So basic something like an index in a traditional database.
So rolling up.
Yeah. So basically, I assume there is no other magic bullet than just streaming to the data and writing it again.
Yeah, you're going to have to. I mean, depending on if you can do this through counters, you might get that type of aggregation in there. Otherwise, you're going to have to write something that will read the data in, roll it up, and query it. And this is where you start to see things like putting things like Spark and Shark kind of on top of Cassandra, and using the kind of Hive-based stuff you get with DSE to do these roll-ups for you. So you do it, but the problem you're always going to find is if you start doing something it's going to be a batch-based roll-up. So you got to think, how real-time do I want my roll-ups to be? But there's no magic thing that's going to do this for you.
Okay, thanks. So let's say that we are writing these. We spoke earlier about like these keys and values, and let's say that there is a set of keys that we keep for a single sensor, but they are being written like randomly, and we would like to get like the latest values of each of them in some one query. Would that work, or should we just like use a cursor that goes backwards in the table, backwards in columns?
I'm confused. Are you talking about doing a range query on the partition key, or a range query?
Well, on these values and keys that we are holding inside sets.
Oh.
How well queryable are those?
Yeah, they are queryable. Actually, you can get into them. I would be cautious on that. I would just get it back and then in-app do it to start.
Okay, so basically, if I were to have a row where the columns would have a set in them, and I would like to find a set value with a certain key. There's the latest one,
An actual index on the so indexing one of the fields in your set to
Yeah,
jump to it.
well, I think indexing all of them would be too disk intensive. But we'd still like to have the latest values. But if there's like an efficient way to do this,
there's no massively efficient way to. But if that was how you were wanting to get at this data, I would denormalize it out of a set into something that I could query directly. I wouldn't start getting into the. I'm typical. The collections in Cassandra are, they're reasonably new. It's getting better and there's more performance in there. But I just naturally I prefer to see it denormalized out. And if you were doing those type of that's a quite complex type of querying. I would dupe my data and I would have, this is how I want it back for this query in a nice set that I can have my stuff in there, and then I would build a separate query table to give me that type of indexing I want on it. So I would explode that set out into something that I can basically, quite similar to what you were doing on your tagging of the URLs, something like that.
Yeah, okay, all right, thanks. So the final question is about what if we don't have a set? We have, for example, Boolean field here. Yeah. And we were trying to. We know about this Boolean field that up to a certain point all the Boolean values are true, and after a certain point they're false. Is there like an efficient way to find where the split point is in time?
So
because if you had like if you had this in a programming language, you would like do a binary search or something like this. But in a database, it does not quite work usually.
So what you're talking about is you're going to have sensor data coming in. Sometimes true, sometimes false.
No, not really. I mean, we know that the Boolean is true or false up to a certain point, after which it just switches the value, and from that point on, every value will be true or false. The other value. So we would have like a split position there, and we would like to find the split position as efficiently as possible. I don't know if it makes sense.
I can't get it in my head. Nah. I'd have to draw it out and figure it out.
Okay, I'll try it again, perhaps a bit more imaginatively. Okay, all right. So let's say that sensor has a value called broken.
Okay.
and basically the sensor can tell you that whether it's broken or not.
Yeah.
And up to a certain point of time, it's not broken. It sends false every time.
Yeah.
We say false in this column. And at some point it breaks, and then it sends true from that point on.
Yeah.
And would it be possible to efficiently find the point of time where it broke without having like a separate process for this?
Yeah, you'd have your value, the broke value as the one of the as a clustering column in your primary key definition.
Okay.
And you would basically then do a predicate on that where it's true.
Okay, but what if there were quite many of these booleans?
It should be okay.
Should be okay. So I can put like 100 different booleans in my clustering columns.
I mean, it's you can. Sorry, say that again.
What if I had like 100 different booleans that work like this in my clustering columns?
You mean what, like a?
Like if I were to have like 100 booleans that showed like, I don't know, 100 different parts that were broken or not. And then I would like to find one of the sensor parts or something that at what point of time that broke.
I don't know. I read that sounds complicated. I'd need to sit down with you and.
Okay, but we should probably do it sometime. I think I should probably stop asking these questions. I mean, I think our use case is a bit too specialized. That's why we actually came out here and try to find out whether Cassandra would work.
I mean, it's all about how you define the partitioning and the clustering of your data on disk, and where you then jump to and what makes it more efficient. I mean, what you're describing to me there. It's very difficult for me to conceptualize it. If it's just the simple single Boolean, I would use that as a clustering column, and then I would do predicates on that.
Yeah.
If it's a slightly richer data set, in there you would just have more columns as part of your clustering. But the problem with that is, which you have to the order of your clustering columns, you can't jump when you're writing your queries. You have to say, if you've got column A, B, C, D as your clustering, you have to go where A is true, B is to get to D. You have to actually traverse the order. You can't just jump to one like that. So what I would do then is, if you did have different ways of wanting to jump around, I would initially think of duping the data, but with sensor data, that's going to be a potential problem.
Yeah, that's what we're facing right now, right? So okay, that was a perfect answer, I guess. But
how in terms of the queries, what's the SLA on the queries? I mean, how quick how quickly do you need to get the data back? Is it like?
Well, we are doing real-time queries at like, say, like 1,000 to 2,000 per second,
Yeah.
And we are querying at least like 100k points out of the dataset at any given time, and they are ordered by timestamps, like from some value in time to some value in time.
What I'd say, the first thing to do is just define each of the type. Give me. We can take this offline actually, but what I would start with is saying, okay, what are the give me every single query that you want to be executing against your data set, and then look at an appropriate model for it. That would be how I'd start looking at that. Offhand, if you're, I would see initially I'd be duping this data based on the way I want to be querying it. If that's not an option, if your SLA on response times is you can have a slower on reads, there are other ways of, essentially, for instance, you could do something like our search piece, which gives you a much more richer, you've got a Lucene index on your column family, you can do very efficiently, but it's obviously not going to be as quick as going native with the Cassandra. So that's your kind of balancing act as to which do I want. Nothing will be as quicker as you duping your data in every possible way you want to be querying it.
Yeah, true. Okay.
And there is no, I think that's going to be the same in any database like this. But you can get Lucene indexes built off it that would give you that, but it's going to be slower.
Yeah. Okay.
And it typically requires more grunt as well on the server side for this, obviously, because it's doing a lot more than Cassandra on its own. It typically needs more CPU and more RAM as well.
Okay. Thanks.
So, but I'm wondering, it's an interesting. I'm sure there's a way of slicing it up. You've got my email address, haven't you?
Yeah, I do. Yeah.
Just ping me an email. Give me an example of the type of queries you want in the data, and I'll knock something up on my blog.
Okay, thank you very much.
And big disclaimer.
Perhaps like one last question, just simple one. So we have a time series database. We have columns for like timestamps.
Mm-hmm.
Can we also do a range query based on by count of those timestamps, like if they are not regular?
You can, but it's not going to be very hugely efficient. I mean, counts are you want to be able to count how many samples of data I have within a range.
No, not really. I would like to, for example, pagination basically.
Yeah.
I would like to get from like the 100,000 to 101,000. And get these by count, like pagination, basically. If I were to list them out on a web page or whatever.
Do you mean like jumping?
Yeah,
ahead? Yeah. No, you can't jump ahead. You can only go forward.
Okay. All right. So I would need to keep a cache on based on the indexes for the different timestamps, and then based on that do some.
You would have to have a query that jumped to the point you want your data returned.
And I would need to know the timestamp.
You could do a range query on the time.
Yeah.
So you could say if it's between a specific date range, then you get the data back.
Yeah. Okay.
And then you paginate it into the app that way.
Okay. All right.
But if you haven't got a predicate in there to jump to where you want to be, you have to obviously stream the whole data in and just get to the point you want to be.
Okay. Thank you very much. And that's all for now. I'm really sorry if these questions are boring or something.
So you said that you can have multiple cluster keys?
Clustering columns.
Yeah, multiple clustering columns. Would that then map out to multiple columns with different column key? I mean, because I come from the previous Thrift world, so the naming sometimes is not...
what I suggest, and this is the thing I always say to anybody: create the table in CQL and then go into the other thing and have a look at it. As soon as you see it, it clicks. It looks like it's doing something unnatural to the storage engine, but it is very natural to the storage engine. Also worth looking at it when you start looking at how collections as well are stored. It's very. I had a similar. Well, how is this? This is gone from a fairly unstructured storage into a structured one. How is this still meeting all the stuff you want? When you have those type of questions, create the table, put some data in it, and then look underneath, and you will see it. There's nothing you wouldn't be probably naturally doing through Thrift. The only advantage, because naturally, why bother? Why don't I just use Thrift based on the same? So the point is, it's being executed. The SQL is being executed closer to your data than the Thrift client is. So that's your win. But under the hoods, it's still the same storage.
Yeah, talking about Thrift and CQL, is there any way of migrating from Thrift to CQL without rebuilding the whole database? If you happen to have or is it enabled? Can we easily, without changing the column families, change from Thrift to CQL and hope that the thing that we made up ourselves will match good enough with your vision of doing columns?
No, I wouldn't. I wouldn't say so. No, I think once you're on that path, you need to be thinking of an engineering effort to switch.
Oh, okay.
I mean, you could, if you're talking about transforming the data from your Thrift into the CQL, then you're into the similar question to the chap there had around bulk loading data. But once you're on Thrift, you are on Thrift. Data still, yeah. I've never really seen that. No. Technically, there might be some weird way of doing it, but I've not tried it. I know your point is, well, surely if it's the same storage way, there's also a bunch of meta information in there as well that you'd probably have to figure out a way of replicating. Yeah. 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 Yeah, well, I think that's the point. It kind of works. If if it does work for you, more power to you and crack on it. But make sure you test it. It's not something. If you're asking, have I seen in a production-heavy environment somebody taking that approach? I haven't seen it. I'd want to be very sure. Ultimately, it is just kind of meta information around what's being stored. So there must be some way of doing it, but I've not done it. Yeah. Lots and lots of things. I mean, they're different things. They're in. I mean, the reason why the reason why the community introduced CQL was, really for two reasons. It was, ease of use. Obviously, it's easier for people to pick up and get running with it. But also, there's compatibility of the various Thrift clients, and being able to guarantee that they'll all, like Hector, etc., will always work with a version of Cassandra. And I have had this several times where, with Hector, where you've upgraded Cassandra, and all of a sudden your version of Hector doesn't work. And that there's the fragmentation around the Thrift approaches versus the kind of, well, this is native to Cassandra, and you got to figure out what's best for you. There is absolutely nothing wrong with Thrift. If you're comfortable with it and using it and it works for you, continue to use it. Don't feel there's some I need to get off Thrift. It's not end of life. It's not finished. There are lots and lots of performance enhancements coming in around Thrift with every release of Cassandra. It's just you now have a choice as to which one you want to get. So don't. I mean, people were typically cautious around multitude of key spaces in early versions of Cassandra because each key space took about 2 megs of memory of RAM on your heap. That's gone now, so you don't have to worry about that. My question would be, why would you not want to have a separate key space for it? I can't think of anything technical as to why that would be an issue in the same key space, but I've not tried it, and I can't think of anything. I can't think of anything technical as to why that would cause problems, but there might very well be something weird in there, but it shouldn't really make much of a difference. The only thing I could think is potentially the key space definition might be a bit funny with that's the only thing I could think of. But in a similar way, and you can drop into Thrift and query the CQL stuff. So you should be able to do it.
Hey Johnny, I do have a question, but first he deserves the mug because he keeps asking. I think it's because of that, because you didn't give him the mug.
Oh, sorry.
Wasn't it? I know you. You are here from the start. I know. But I do have a question. In our cluster, we do have 8 physical nodes, and they're quite beefy nodes. We have like 60-something gigs of memory in each one, and all SSD. And we are considering actually putting virtualizing them and creating smaller nodes, because the repairs take a lot of time, and well, there's a lot of downsides. But my question is, what do you think it's suitable size in specs for a virtual node?
You mean a virtualized node or
a virtualized node? I mean, if we take all of 8 nodes and virtualize them, what do you think it should be? Is it like 4 gigs of memory? Okay.
No,
8 gigs of memory? Okay.
So there's 2 issues with there's a multitude of issues with virtualization and Cassandra. The first issue is storage, is your disks. Yeah. If you're sharing disks between nodes, you need, and particularly if you're using spinning disks, that's going to cause you all sorts of problems. Because
it's all SSD in all of them.
I'd still be very cautious about sharing the same physical disk between my virtualized nodes. So shared storage and Cassandra is, I have to say, with the except of Google Compute, which I'm desperate to know how they're doing it, but shared storage and Cassandra is not a good idea. So first thing to storage. The next thing is going to be CPU. If you're, again, contention on CPU cores, I would say don't do that as well. So you need to make sure that they're not contending for CPU, because if you get to a state where you have a noisy neighbor that's going into a fairly heavy compaction cycle, it will then start sucking up resources from the other nodes, because it's going to be CPU intensive. But what also that will give you is an unpredictability in throughput, because writes are CPU bound. You will have variable throughput if you start containing on resources in CPU. So don't share the disks, don't share the CPU, and then you're into RAM. 8 gigs of RAM. I mean, the heap allocation in Cassandra defaults to 8 gigs, but that doesn't mean it's using off-heap memory as well. It's using a lot of off-heap memory. So as much RAM as you can throw at Cassandra is going to be the better.
So the thing is that we have 64 gigs of mem.
That's
16 physical cores and 8 boxes of those. All SSD, and the things that, okay, we can virtualize them and put maybe 2 nodes or 4 nodes in each.
I certainly wouldn't go for 4 nodes on that. With 64 gigs of RAM, again, it'll come down to your throughput. I mean, I would, my base point when somebody speaks to me about what kind of hardware do I need is there. I usually would start at 64 gigs of RAM, maybe drop it down to 32 if they're worried about it. But RAM is very cheap, so the more RAM you've got at it, the better. Cores, the sweet spot on price for cores is typically about 8 cores per Cassandra node. You can drop down lower if you want. I see people going down to 4 cores per node. But I mean, there's no, don't over allocate the resources on your server, you will. The worst thing that will happen is a noisy neighbor or a fairly that will start affecting your performance. But the biggest problem with virtualized nodes is actually availability as well, because if you think about it, if I have a replication factor of 3, how do I know my data has been replicated across different different physical servers if I'm in a virtualized environment? And then people start going, okay, well I'll allocate each physical server as a data center.
I was thinking about that.
And then you're into other problems with that. Is then what do I do about my data centers when I want to have data centers? So there is. I either raised it or I'm about. Obviously you're not the first person to do this and ask about this. I mean, virtualization is something historically I think Cassandra's not. We've basically it's not a good idea, but we work in AWS. It's a virtualized environment. But you notice in AWS, when we give the recommended settings, it's SSDs, it's don't use ephemeral storage, don't use shared storage. You're basically dedicating as much.
The reason behind is that we see problems in the compactation and all the cleanup things, all the maintenance stuff.
So are you using vNodes or are you not using vNodes?
It's that we have a very large amount of data per node. It's somewhere between 800 to 1 terabyte of data per node. So
that, as data density goes, that's not. So previous versions of Cassandra, a terabyte would be. You're on
1.2.13.
1.2.13. 1.2.13. A terabyte should be fine per physical. Data density of terabytes. It's reasonably okay. I would start thinking maybe you're TTLing a lot of data, aren't you?
Yeah.
And that's probably why your compaction's fairly heavy.
Well, I have one question that leads on regarding compaction. Is we've had to cut back on the concurrent compactors to reduce because we were having garbage collection issues.
Okay.
Like the garbage collection, it was running like full cycles very often, and now that is much better, but it's still like sometimes a cycle can still go like up to 16 seconds. Like today I've seen 16 seconds. And I wanted to ask
on GC?
Yeah, full GC.
Wow.
And I wanted to ask you like what could we do further to kind of reduce that,
Data density.
Would a bigger heap be
No, because there's more to sweep then. So if you have 8 gigs heap is a lot of thought's gone into the default settings on this. You start to get up, if you go to 12 gigs heap, you're going to start seeing the cost of sweeping them. They're going to be you're going to have more GCing. Are you using size tiered or level tiered?
Yeah, size tiered.
And you're on SSDs?
Yes.
And you're using TTLs?
Yeah.
So you've got highly mutable data on SSDs. I would suggest looking at leveled compaction. See if that improves things for you.
Okay.
That, based on my default answer for you would have been, if you're using SSDs and you're highly mutable data, I would be looking at level tiered by default. You can also, you've got multi-threaded compaction as well. You can potentially enable that or disable that depending on where you see the issue happening.
Yeah, we had it enabled, like we had it completely optimized to speed up the compactions, and then we've gone the other way now. We've tuned that all down to get better garbage collection performance.
I would look at level tiered compaction.
Okay.
See if that improves things. If not, we can figure it out.
Okay, thanks.
$1 million questions. Based on this, do you predict any problems migrating to Cassandra 2.0?
2.0. So Cassandra 2, things to be obviously Java 7's now mandatory. So you have to make sure you're using JDK 7. You can on 1.2.13 you can be on 6 or 7, but with Cassandra 2 it has to be 7. Other than that, it'll be quicker. It'll be more performant. There's a lot of performance improvements with Cassandra, and when Cassandra 2.1, big emphasis on 2.1 is performance as well. But I wouldn't see anything. I think you'd get a performance improvement, particularly with on the memory side, because every release of Cassandra, more goes off heap. So if you're seeing big pauses on GC, you will see less. There's also, have you got GC logging enabled?
Yeah, we've got all of that.
Yeah.
All that, whatever logging options were available, they're all on.
Yeah. Well, that might also be a reason why you're seeing performance. Yeah.
Sorry, one more question is that, I know that there is the repair option is there in the enterprise version of Ops Center, but do you know of any open source tools to help orchestrate repairs across the cluster?
Not really.
Yeah,
I mean, so repairs, yeah. So it's just you can cron tab it to run within the GC base. Are you doing it with the -PR or? Well, I mean that's you're doing it right. I mean, and you're walking the ring, doing the repair on there, and that's within your GC Grace.
Yeah, but that's the thing is we have these big nodes, so it takes long to do the repairs, and we were thinking of how to kind of speed them up. And
you could, because you've got sub-range repairs as well, which because you're not using vnodes would be a lot easier to do. I'll dig it out. There's a really good. We've actually looked at our blog. There's a whole thing on sub-range repairs.
Okay.
You might find that speeds things up, but you're not. There's nothing you're doing that would say I'm going to have a particularly erroneous, specific issue around repairs. You might find when you switch, if you did look at switching compaction, you might find your repairs start to get a little bit more efficient. But I would definitely be first thing. How are you on TP stats? Are you seeing
no issues?
Nothing blocked,
pending,
nothing dropped.
No. Yeah, on the something is dropped. What was it?
Okay, so the drop.
It's like a very low number.
Anything dropped is bad. Yeah, okay. Dropped is like the worst thing to see.
Yeah.
So I would start looking at what's dropped.
Yeah.
You said you're using RAID 0.
Yeah.
So first thing I'd say, if you're seeing, for instance, if it's flush writer being backing up with pending or dropped, that probably means to me that your disks are not configured optimally if you're using SSDs. Make sure what flavor of Linux are you on, or Debian? So make sure you've done all the kernel flags and stuff to make the operating system aware you're using solid state disks. I'd also start looking at your RAID controller as well. Are there any optimizations I can do around your RAID controller? And there's if compaction, disk, yeah. That's your first port. If you've got SSDs, you should be flying. And if could be the repairs, could be the Merkle tree generation, but even that, you're not doing anything particularly crazy. But tell me look at your TP stats. What's backing up?
So
what's being blocked? Yeah.
Okay, great, thanks.
But I mean, to me, everything I'd say, not everything. That's general. I'd say easily half of the problems I get seen are disks. Compaction's disk heavy, repairs are disk heavy, and mount point. Oh, another one. Sorry. How many SATA? Do you have one SATA controller, or have you got one per disk?
I don't know about the hardware.
Because you sometimes see if you've got one SATA controller, that can also be a bottleneck on throughput for your SSDs. We've seen some very interesting. We've got some crazy brains looking at really optimizing hardware, and that's a £30 controller can give you if that's the throughput you're hitting, it's just that 30 quid, one per disk, can often give you just a boom straight through. Look at your RAID. How do you need a RAID controller? Yeah, I mean, can you pin hot tables to disks and then put other tables that you're not so worried about to other disks? If that's the problem, there's so many ways you can get your stuff tuned.
Okay.
A few more questions about infrastructure. We are planning our cluster, and we're considering using AWS-like environment. At the same time, you said that virtualization is a bad thing. For example, if we have about, we have to consider about 10 terabytes plus data. Yep. And can you give some best practices for AWS type environment? For example, should we take fewer big nodes with lots of memory, or a lot of small nodes, or what sort of storage should we choose? Or is it drop AWS and have your own hardware?
No. I mean, we as I said, so let me call it, virtualization is not a bad thing. It's just not as good as tin. Yeah. So you need to provision more to make up for this. With AWS, I mean, Cassandra's, all over AWS. So you're not going to have any issues going on to AWS. If you look at our documentation, there's a whole bunch of recommendations for what you need to set up in AWS, what the optimal hardware, the optimal instance configuration is. But basically SSDs and an extra large instance is usually where you'd want to get to. You're then into don't use EBS. Do not use EBS. Use ephemeral storage because it's shared storage. And I'd also, not that I don't work for Google, but I would seriously have a look at Google Compute if you're looking at infrastructure as a service. We're seeing some extremely impressive throughput on Google Compute stuff. Like we're all scratching our heads as to how they're doing it. So don't, alternatively use both. That's the other option, is have hybrid models for infrastructure, people running on their own tin, cloud, multiple cloud providers. I worked a couple of years back, and we built something that was split between our own tin, AWS, and Rackspace, with Cassandra just replicating between all three of them, because we didn't want to have buy-in to a single provider. We wanted to be able to switch out when necessary. So AWS is very rich in what it does, so I like it. I use it all the time. But I would have a look at Google Compute, particularly the storage bit. It's exceptional. You might find, and getting back to your 10 terabytes of data, that's pretty small. That's not a huge amount of data. Data density on AWS you would want to have it lower than you would on your own tin. To me, a terabyte would be a little bit, might be pushing it a little on AWS, but that will come down to the type of workload you're doing. If it's all writes, none of your data is mutable, then you might be okay with a greater data density. If it's mutable data a lot, you might want to reduce the data density per node to make up for that. Other consideration on Amazon is the network as well. Are you going to be multi-region or
single at the moment?
So just there's people always forget this one. There's a piece of configuration in Cassandra YAML called I don't even know how to pronounce PHI_convict_threshold. And make sure you increase that when you're on AWS. This is how Cassandra its tolerance to flapping, and what the kind of consensus within gossip saying, well, this node, I think it's up, I think it's not, I think it's down, who wins? You will want to increase that on AWS as well. I think it's at 8 or 5 by default. You probably want to make it 10. Everybody forgets to do this, so that's why I'm saying it. Because you will hints. Do you know what hints are? So when your Cassandra cluster marks a node as, I think this node is offline. So a write comes into your arbitrary coordinator node. You've got a replication factor of 3. It will go, yeah, okay, this replica this node. Ooh, this node's not available. I'll store a hint on that coordinator. So when that node comes back, I replay that hint to it. And that's what you're doing with hints. So when you have flapping nodes a lot, you start to get lots of hints. And hints are bad because you're taking up resources. Look at why you're getting hints. Don't just think, well, Cassandra's going to, Cassandra will handle it for you, but it's doing it at the cost of something else it should be doing. So don't ignore hints, particularly with AWS. Sometimes for no apparent reason, this node is just all over the shop, and Amazon will say no, and it could be many things. Sometimes it's better just destroy it and start with a clean node and just repair your cluster and suck the data in. Don't get overly wrapped up in fixing one node. Don't throw things away arbitrarily, but don't sell. If one node's giving you lots of problems, just destroy it and start again. But yeah, AWS is. This is one of the interesting ones. You had Dynamo and DynamoDB and AWS. So Dynamo was it reInvent recently. They were saying, yes, we've got up to was it like I can't even remember the number. It was the amount of throughput they're able to get through DynamoDB, through Dynamo, not one specific, through DynamoDB was. Let me see if I got the data. But I'll dig out the data. But it was Netflix's entire throughput in terms of writes to Cassandra was like a factor of 10, 20 just on their Cassandra instances, what they were getting through DynamoDB. So Cassandra runs very well on AWS. It's don't be worried about it, but do look at Google Compute.
Thank you.
They're going to be a big. I'm blown away by them. So, and in our documentation, everything's there for how what the firewall configurations have to be, what ports, everything like that. So just follow it. I'm here all night.
So no more questions? That's it? It's not all night after all.
I need to get some sleep.
Okay, guys, thank you very much. You can still chat with him.
Yeah.
And us, of course. Thanks for coming. And thanks, Esko.